Physicists have waited 100 years since 1916 for this photograph.
Due to extensive research over the past few decades, we've transitioned from knowing absolutely nothing about black holes to learning more about them up close and personal. And now things have become even more astonishing. Michio Kaku has just announced that we've finally glimpsed what's inside a black hole. This groundbreaking information sheds light on details that the scientific community might have missed all along. Join us as we delve deeper into black holes and unveil what's inside space's big enigma. Before we dive into the specifics of what Michio Kaku discovered about black holes, we need to discuss the basics. Even though many of us have some understanding of what black holes are, there are still significant gaps in accurate information. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept was purely theoretical. It took another 50 years for the scientific community to find evidence that black holes actually exist. In the 1960s, astronomers studying the Cygnus constellation noticed an unusually bright blue star emitting X-rays. This star wasn't stationary. It was orbiting a massive, unseen object. Further investigation revealed that the X-rays weren't just moving independently, but were being sucked into this invisible entity around which they orbited. This led to the term black hole. This discovery was significant because it provided proof that black holes are real and not just figments of Einstein's imagination. While this was an exciting development, it also meant that there was an unknown and potentially dangerous entity in space that we urgently needed to understand better. Scientists worldwide began intensive research. The black hole was named Cygnus X1 and is located in the Cygnus constellation, about 6,000 light-years from Earth. This was no minor discovery. It's about 14 times brighter than the Sun and incredibly dense, resulting in a strong gravitational pull. The gravity is so intense that not even light can escape, hence the term black hole. The concept of a black hole is both fascinating and terrifying. A region in space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close is pulled in, never to be seen again. This inherent danger makes it even more crucial to learn everything we can about them. Was this the end of our journey, or were we just at the beginning? The answer turned out to be the latter. Following the discovery of Cygnus X1, scientists began searching for other black holes. They found that there might be over 100 million black holes in the Milky Way galaxy alone. However, because they are incredibly difficult to detect, we still don't have an exact number. Nevertheless, it's evident that there are several million black holes in our own galaxy, which makes studying them even more important. Let's break it down. The primary concern with black holes is gravity. Their gravitational pull is so intense that anything entering them is compressed astronomically until it becomes a singularity. In simpler terms, black holes act like cosmic vacuum cleaners, sucking in everything nearby. One of the most alarming aspects of black hole research is that if someone were to fall into one, they would be stretched to such an extreme that they become a single line of atoms. This process, known as spaghettification, would happen slowly, and the person would die before reaching their final form. Needless to say, no one should be venturing into one. But given their abundance, could we be in danger? Despite the closest black hole to Earth being about 1,500 light-years away, it's still close enough to raise questions and concerns. In 2021, scientists were able to release the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed over several nights, and with each image, researchers gathered more and more evidence. They had to stitch individual photos together to fill in the gaps, which allowed them to determine that black holes consist of 3 layers. They aren't just simple voids as many people believe. To even reach the nothingness at the center of a black hole, you have to pass through the first 2 layers. The first layer is called the event horizon. It's the point of no return. Once you cross it, there's no turning back, and you will be sucked into the black hole. The situation only worsens from there. The second layer is the photon sphere, where light itself orbits the black hole. Any light entering this region becomes trapped and cannot escape the gravitational pull. Finally, we reach the third layer, the singularity. This is where everything entering the black hole is compressed infinitely until it becomes a singularity. The singularity is a point in space-time where the laws of physics as we know them break down, and we cannot predict what happens next. At this point, the density is infinite, and our understanding of physics ceases to apply. What makes this even more complicated is that every black hole is entirely different from the last. While they generally follow the same three-layer concept, their behaviors can vary greatly. If this were any other astronomical phenomenon, we could simply use telescopes to study it in detail. However, with black holes, direct observation isn't feasible. Scientists can only study them indirectly by observing the radiation they emit and the gas and dust that surround them. Sending a probe like Voyager into a black hole isn't possible because anything crossing the event horizon is pulled toward the singularity and compressed into an infinitely small point. You can't justify spending billions of dollars on probes that will be destroyed before providing any data. Because of this limitation, scientists are forced to study these objects in a two-dimensional way, even though they are three-dimensional phenomena. To make matters more challenging, each black hole's uniqueness and the breakdown of physical laws within them mean that traditional scientific methods don't fully apply. Despite these challenges, researchers have been busy formulating various theories and explanations about black holes, each more intriguing than the last. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts all its fuel, it can no longer produce enough energy to counteract gravity's inward pull. As a result, the star begins to collapse in on itself, becoming smaller and denser. If the star is massive enough, this process can continue until it becomes a singularity. To understand black holes more deeply, NASA scientists turned their attention to the core of the galaxy, M87. Astronomers observed a super-powerful whirlpool of extremely hot hydrogen gas, spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of this spinning disk should have caused it to fly apart violently in all directions, but it didn't. Scientists deduced that a colossal mass must be concentrated at the galaxy's center to prevent this from happening. This massive object, weighing as much as 2 to 3 billion suns, could only be a black hole. But that's not the only theory involving spinning black holes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr showed that a spinning black hole wouldn't collapse into a single point, but into a ring of fire or a thin disk. This disk spins so rapidly that centrifugal forces prevent it from collapsing. This spinning disk of matter is called the ergosphere, the region surrounding the black hole where the laws of physics start to break down. The most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed into oblivion, one might be sucked through a tunnel and shot out of a white hole in a parallel universe. To grasp how this works, we need to consider the concept of space-time. In Einstein's theory, space and time are not separate entities but are interconnected, forming a four-dimensional fabric known as space-time. Objects with mass distort this fabric, creating a gravitational field that causes other objects to move toward them. Imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this represents how objects move through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole, a shortcut through space-time that connects two distant points instantly. Wormholes aren't just science fiction. They are actual predictions of general relativity, although none have been observed directly. The reason is that wormholes are inherently unstable and would collapse almost immediately. But the existence of an Einstein-Rosen bridge would mean that black holes might not just be cosmic vacuum cleaners, but could also be portals to other regions of space-time. So, could we use a wormhole to travel through space and time? Unfortunately, the answer is probably no. Not yet, anyway. Even if we could stabilize a wormhole, it's unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is the absolute limit for how fast anything can travel through space-time. Nevertheless, the theory of wormholes and black holes as pathways to other parts of the universe, or even different times, has been a subject of fascination and speculation among physicists for decades. The idea that there might be shortcuts through the fabric of space-time, allowing travel through great distances or even into the past, could be revolutionary if we could actually achieve it. One of the most intriguing concepts in this area of study is the Kerr wormhole, named after Roy Kerr. This type of wormhole is essentially a hypothetical tunnel through space-time that could connect two distant points, such as two different universes or even two different times within the same universe. The Kerr wormhole is often visualized as a ring-shaped portal, similar to the looking glass in the story of Alice in Wonderland. Walking through the looking glass transported Alice to a world where animals spoke in riddles and logic didn't always apply. In the same way, passing through the Kerr ring could potentially transport a traveler to another universe or another time, where the laws of physics might be very different from those we are familiar with. But at the destination, that could be considered normal. While the idea of wormholes as a means of interstellar travel or time travel is certainly exciting, it's also a subject of controversy and debate among physicists. Some have pointed out that wormholes, and particularly Kerr wormholes, might be unstable or impossible to traverse due to the intense radiation and subatomic forces surrounding their entrances. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity and not the quantum forces that govern radiation and subatomic particles. To truly understand the nature of these phenomena, a new theory is needed that can unite the laws of gravity with the quantum theory of radiation. In the scientific community, this is called a theory of everything, a single theory that can unite both Einstein's theory of gravity and quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for decades. Among the various versions of what this could be, the one that has shown the most promise is superstring theory. Superstring theory unites gravity with the theory of radiation by proposing that subatomic particles are actually tiny vibrating strings and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the fascinating things about superstring theory is that as a string moves in time, it warps the fabric of space around it, producing black holes, wormholes, and other exotic solutions to Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with quantum theory, but also explains many of the mysterious phenomena that we observe in the universe. However, there's something about this theory that complicates how simple it might sound at first, but in a way makes more sense too. Superstring theory requires 10 dimensions of space-time in which the strings can vibrate. This is quite different from the 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. It's difficult to imagine what these extra dimensions might be like, but physicists have developed some conceptual models to help us understand. Consider a 2-dimensional pond inhabited by fish that are only aware of length and width. To these fish, there is no such thing as height, and they can't even imagine what it might be like to live in a 3-dimensional world. But if rain falls on the pond and causes ripples, the fish can see the effects of the 3rd dimension even if they can't actually experience it directly. Similarly, physicists believe that we can't see the extra dimensions of space-time directly, but we can observe their effects on the world that we experience. In particular, the vibrations of the strings in superstring theory can produce waves of energy that travel through the extra dimensions of space-time. These waves can manifest themselves as particles with different properties, such as mass and charge. In this way, superstring theory can potentially explain all of the particles and forces that we observe in the universe, including gravity. But there is a catch. The extra dimensions of space-time that superstring theory requires are so small that we can't really study them directly. The most precise measurements that we can make in our laboratories only use the 4 dimensions of space-time that we are familiar with: length, width, depth, and time. So how can we even know that the extra dimensions exist? One possibility is that the extra dimensions are curled up so tightly that they are invisible to us. Imagine a sheet of paper that has been tightly rolled up into a cylinder. If you were an ant walking along the surface of the paper, you might not even notice that the paper is curved. Similarly, the extra dimensions of space-time in superstring theory could be curled up into tiny loops or spirals that are invisible to us, even though they affect the behavior of the strings that vibrate in them. Another possibility is that the extra dimensions were more visible at the beginning of the universe during the Big Bang. According to some versions of superstring theory, the universe began in a state of 10-dimensional space-time with all of the dimensions equally visible. As the universe expanded and cooled, the extra dimensions began to collapse and curl up, leaving us with the 4 dimensions that we observe today. If this scenario is correct, then we might be able to detect traces of the extra dimensions around us. The mathematics involved in superstring theory is incredibly complex. It's opened up entirely new areas of mathematics that were previously unexplored. However, the challenge of solving the problem of a quantum black hole has proven to be elusive. While many physicists have tried to tackle this problem, no one has yet been able to do so fully. Edward Witten of the Institute for Advanced Study at Princeton has called superstring theory 21st century physics that fell accidentally into the 20th century. Recently, several groups of physicists independently announced a significant breakthrough. They found that string theory could completely solve the problem of a quantum black hole, although only in 2 dimensions, not 10. Many physicists believe that it's only a matter of time before someone cracks this problem, given that the equations involved are well-defined, if difficult to solve. Until then, it's still too early to buy tickets for intergalactic travel or time-traveling expeditions, at least when it comes to black holes. With all of this, one thing is clear. There are simply too many questions and even more solutions to these problems. Michio Kaku has explained how one might determine the real answer among all the theories. He said that it's important to note that the problem of infinite answers isn't unique to string theory. In fact, many great theories have an infinite number of solutions. For example, Newton's laws can predict the motion of various objects, from rocks to rocket ships. But you need to specify what it is you're trying to explain before you can predict its motion. These specifications are called initial conditions. Similarly, in string theory, you need to tell the theory what it's describing. But unlike other theories, the initial conditions of string theory are the Big Bang itself. This means that you have to specify the conditions of the Big Bang at the instant it was created, which are currently unknown. There are a couple of ways to approach this problem. One possibility is to experimentally find the initial conditions at the instant of the Big Bang and then let string theory describe how the universe evolves from there. There are already solutions of string theory that describe the evolution of our universe since the Big Bang, based on some reasonable estimates of its nature. This is a significant achievement. Another more ambitious path is to demand that string theory selects its own initial conditions. That approach is a little more complicated and less likely too. So in a way, we've already narrowed things down significantly. But here, Michio Kaku offers another perspective. Maybe the Big Bang wasn't really all that big, after all. He says it wasn't a massive explosion, as many might think. It also didn't make a loud noise like one might expect from a bang. The Big Bang theory doesn't provide an explanation for what caused the supposed bang or how it occurred. It simply states that it did happen. The truth is, we need a theory that can account for what happened before the Big Bang. This is where string theory comes in. According to this theory, our universe might have been formed from the collision of 2 separate universes, or it could have emerged from another universe, like a baby being born from its mother. This connection between universes is called a wormhole, which is like a tube connecting 2 bubbles. It's possible that we may have already discovered evidence of this umbilical cord that connected our universe to another. In a way, we could just be living inside a black hole this whole time but not know it. Think about it. Because we exist in 4 dimensions and can't see anything beyond them, it's possible that we're actually in a black hole, and the black holes we're studying are actually wormholes to these other dimensions. Do you think there could be truth to that theory? Let us know in the comments below. If you like this video, please give it a thumbs up, and we'll see you in the next one.
James Webb Space Telescope has hardly opened its eyes. and the universe is new.
The telescope itself has to be extremely cold.
NASA's James Webb Space Telescope, humanity's most advanced observatory, has scarcely begun its journey of cosmic exploration, and already the universe appears more enigmatic and breathtaking than we ever imagined. Scientists have recently uncovered a colossal ring-shaped structure in space, so immense that it challenges our understanding of cosmic formation. Yet just as we stood on the brink of groundbreaking discoveries, an unsettling event has cast a shadow over the telescope's achievements. During an ambitious observational campaign targeting Proxima b, a potentially habitable exoplanet orbiting our closest stellar neighbor, the James Webb Space Telescope mysteriously went dark. This sudden loss of communication has left scientists and engineers scrambling for answers. The telescope's abrupt silence raises concerns not only about the fate of this billion-dollar instrument, but also about what it might have discovered before going offline. Proxima b, situated just over 4 light-years away in the Proxima Centauri system, has long captivated astronomers. As an exoplanet residing within its star's habitable zone, it presents the tantalizing possibility of liquid water, and, by extension, life on its surface. Equipped with unparalleled capabilities to detect the faintest signals across multiple wavelengths, the James Webb Space Telescope aimed to probe Proxima b's atmosphere in unprecedented detail. The goal was to search for biosignatures, geological activity, or any phenomena that could indicate the presence of life or a unique planetary environment. The observational campaign began with high hopes and considerable public interest. Initial data hinted at anomalies in the planet's atmospheric composition, sparking excitement within the scientific community. The telescope registered peculiar spectral lines that didn't match any known chemical compounds typically found in exoplanetary atmospheres. Scientists eagerly awaited further data to decipher these anomalies, speculating on explanations that range from novel chemical processes to the possibility of artificial structures. However, before a clear understanding could emerge, the telescope abruptly lost contact with mission control. The communication blackout occurred during a high-priority transmission window when crucial data was being relayed back to Earth. The sudden silence left operators bewildered. All systems had been functioning optimally moments before. Ground-based teams immediately initiated diagnostic procedures to determine the cause of the loss, but no definitive explanation surfaced. The telescope's systems appeared intact, and there were no signs of technical malfunction. This silence created a void quickly filled with speculation, not only about the technical nature of the failure, but also about the data the telescope might have collected on Proxima b. The implications are profound. It's not merely the loss of a vital piece of equipment, but the fact that it happened amidst one of the most promising investigations in modern astronomy. The data being collected could have reshaped our understanding of our place in the universe. One leading theory among scientists is that the telescope encountered an unexpected cosmic phenomenon near Proxima b, a natural but powerful event that interfered with its communication systems. Cosmic occurrences like intense solar flares, gamma-ray bursts, or magnetic storms are known risks to space instruments. Proxima Centauri, a red dwarf star, is particularly volatile, frequently emitting powerful solar flares that could impact nearby planets and, potentially, instruments observing them. If the telescope was exposed to a sudden surge of radiation or electromagnetic interference, it might have damaged its systems or disrupted communications. Alternatively, some propose that the shutdown resulted from an anomaly in the telescope's software or onboard systems, triggered by the specific data it was processing. In this scenario, the spectral data from Proxima b might have contained unforeseen patterns that interfered with the telescope's data processing algorithms, causing a cascading failure. While this theory is speculative, it raises questions about whether the data itself, rather than an external cosmic event, contributed to the malfunction. If true, this would prompt inquiries into the nature of the detected signals and what could generate them. More controversially, some suggest the blackout wasn't a coincidence. They propose that an intentional signal or structure on Proxima b somehow disrupted the telescope's systems. While such claims verge on science fiction, they can't be entirely dismissed, given our limited understanding of extraterrestrial environments. In the realm where natural phenomena and potential artificiality blur, the possibility of an unknown force or technology interfering with the telescope becomes a thought-provoking, if unsettling, prospect. Proxima B's very nature adds to the mystery. As one of the closest exoplanets to Earth and a prime candidate for habitability, it's always been viewed as a stepping stone in the search for extraterrestrial life. If signs of advanced technology or artificial structures exist beyond our solar system, Proxima b would be a logical place to find them. The exoplanet's proximity and its location in the habitable zone make it one of the few places where conditions necessary for life might be met. Thus, any unusual signals or structures found there would not only be unprecedented, but could have profound implications for our understanding of the universe. The possibility of finding evidence of life or extraterrestrial technology on Proxima b is a notion that has captured human imagination for decades. With powerful telescopes like the James Webb, we finally possess the means to investigate these ideas in detail. However, the thought that the telescope may have encountered something so strange that it disrupted its operations invites more questions than answers. What if the telescope had indeed captured definitive evidence of something beyond our understanding? What if the data it was collecting hinted at a form of life or a structure that defied current scientific paradigms? Such an event would not only be groundbreaking, but potentially paradigm-shifting, challenging our assumptions about life, intelligence, and technology in the cosmos. The scientific implications extend beyond biology and planetary science. If the anomalies detected in Proxima b's atmosphere were caused by biological processes, they could reveal unknown mechanisms of life existing under conditions different from Earth's. Alternatively, if they resulted from non-biological processes, they might point to new geological or chemical phenomena yet to be understood. These findings could force a reassessment of how we define habitable zones, potentially broadening the search for life to include more extreme environments around other stars. Should it turn out that the telescope detected some form of artificial structure or signal, the implications would be even more staggering. Humanity's place in the cosmos would have to be reevaluated, as the discovery of extraterrestrial technology would indicate that intelligence may not be unique to Earth. Such a revelation would challenge what we consider civilization and might lead to a reevaluation of technologies and sciences we believe are the pinnacle of human achievement. However, the prospect of such discoveries remains hypothetical. The actual cause behind the telescope's blackout is still unknown, and it's possible it was merely a coincidental technical failure unrelated to the data being collected. Yet the timing invites deeper contemplation. It challenges scientists to confront the limits of current technology and raises questions about what could happen if humanity were to encounter evidence of extraterrestrial life or advanced technology in a direct and unambiguous manner. Would our current scientific paradigms be equipped to handle such a discovery, or would it require a complete overhaul of our understanding of reality? In the immediate aftermath of the telescope's sudden silence, there's been renewed interest in establishing more resilient communication systems and redundancy in future space missions. The incident has exposed vulnerabilities in current exploration methodologies, highlighting the need for systems that can function even if primary communication channels are lost. It has also sparked calls for greater collaboration between space agencies, as a collective effort may be required to investigate and interpret such mysterious phenomena. As the investigation into the blackout continues, the incident has reignited public interest in space exploration. It serves as a reminder that despite all technological advancements, the cosmos remains a place full of mysteries and potential surprises. The unknown can be both a source of fear and a wellspring of curiosity. The idea that the universe might harbor life or advanced technology beyond Earth remains a driving force behind humanity's desire to explore. The telescope's mysterious blackout, rather than dissuading further investigation, has deepened the desire to uncover the secrets of Proxima b and similar exoplanets. This incident is not just an isolated technical setback, it's a reminder of the challenges faced when exploring the frontiers of the unknown. Proxima b, while close in cosmic terms, is still far beyond the reach of any crewed mission in the foreseeable future. The information gathered from such a distant target is inherently limited by the tools and methodologies used. We rely on spectral analysis to understand the composition of exoplanetary atmospheres, but this technique can only provide indirect evidence of what might exist on a world many light years away. Spectral anomalies or unusual data patterns can suggest possibilities, but they rarely offer definitive answers. The peculiar signals detected on Proxima b before the blackout exemplify this limitation. They point towards something unusual, but without more data, the nature of that something remains a tantalizing enigma. The questions arising from this incident go beyond technical troubleshooting or astrophysical curiosity. They touch upon philosophical considerations about humanity's readiness to confront evidence of extraterrestrial life, should it be found. If the telescope did capture data hinting at life or technological artifacts on Proxima b, it wouldn't be the first time scientific evidence has forced society to grapple with uncomfortable new realities. The history of science is filled with instances where new discoveries have upended established views, leading to intense debates and paradigm shifts. The discovery of extraterrestrial life, or even evidence suggesting the possibility, would likely be one of the most profound shifts in human history. The mere possibility that advanced life could exist on Proxima b raises intriguing questions about how such life would manifest. Would it resemble Earth-based biology, following the same chemical and molecular principles, or represent something entirely alien to our understanding? The anomalies detected could correspond to life forms that don't conform to our expectations of carbon-based, water-dependent biology. They might utilize alternative biochemistries or inhabit atmospheric layers rather than planetary surfaces. If life on Proxima b follows different biological principles, it could signify that life is a far more versatile and adaptable phenomenon than currently believed. On the other hand, if the data indicates technological signatures, the implications would be even more far-reaching. A technological civilization on Proxima b would suggest that life is abundant in the universe and that intelligence and the development of complex societies are not unique to Earth. It would challenge the Great Filter hypothesis, the idea that certain steps in the evolution of life are exceptionally rare, serving as barriers to the emergence of intelligent species. If artifacts or signals of non-natural origin were detected, it might suggest that the Great Filter lies ahead of us, presenting existential risks that all advanced civilizations must navigate. Should there be indications of technology on Proxima b, new questions arise. How would a civilization on a planet orbiting a red dwarf star with vastly different environmental conditions develop? Proxima Centauri emits only a fraction of the light our sun provides, and the planet is subjected to intense stellar flares. These conditions would shape any potential technological advancements in ways that differ dramatically from human civilization. A civilization on Proxima b might need extraordinary measures for shielding against radiation, possibly leading to unique materials or energy harnessing techniques. Their cultural and technological priorities might revolve around surviving extreme space weather, resulting in innovations we've yet to imagine. The notion that life or technology on Proxima b could influence the telescope's operations through direct interference, intentional or otherwise, enters speculative territory, but can't be dismissed outright given the telescope's sudden loss of communication. Some theories suggest advanced civilizations might manipulate electromagnetic signals or use cloaking technologies that interfere with remote observations. If anomalies were caused by artificial means, it would open a new field focused on recognizing and understanding non-terrestrial technological artifacts. Even if no direct evidence of life or technology emerges, the investigation into the blackout and its implications can lead to valuable scientific and philosophical insights. One such insight relates to the need for caution in interpreting data from exoplanets, particularly those within habitable zones. The search for extraterrestrial life is inherently biased by our understanding of life on Earth, limited to a single biosphere. Researchers must expand their frameworks for detecting and identifying signs of life beyond familiar patterns of carbon-based chemistry, atmospheric oxygen, and liquid water. Anomalies that don't conform to these patterns may hold the key to discovering alternative forms of life, provided scientists are open to exploring unconventional explanations. The blackout incident may also influence future space exploration missions, emphasizing the importance of diversifying observational strategies. As technology advances, telescopes and probes will increasingly need to operate autonomously, employing artificial intelligence to make decisions when communication with Earth is compromised. The loss of the telescope during its observations of Proxima b highlights the need for robust fail-safes and more adaptable systems that can continue to collect data even when contact is lost. This could involve developing new ways to transmit information across greater distances or implementing automated protocols that allow space instruments to prioritize and store data. Moreover, the incident underscores the necessity of multi-mission collaboration. Telescopes like Hubble and future missions, such as the Nancy Grace Roman Space Telescope, could be employed in tandem to cross-check findings, ensuring no single point of failure jeopardizes an entire line of inquiry. Agency cooperation among NASA, ESA, and other international organizations would enhance data sharing capabilities, verifying important discoveries through multiple independent observations. This coordinated approach would improve the resilience of space science, making the search for life beyond Earth less susceptible to the loss of a single instrument. Such a diversified strategy could also foster innovation by encouraging the development of specialized, smaller-scale technologies designed to target specific types of data or phenomena. On a broader scale, the mystery surrounding the telescope's blackout raises questions about the inherent risks of pushing the boundaries of human knowledge. Exploring the unknown involves uncertainty, and setbacks like these remind us of the unpredictable nature of space exploration. Yet it's precisely these risks that make the endeavor worthwhile. The potential rewards, unlocking the secrets of the universe, discovering life beyond Earth, or encountering signs of other civilizations, are too significant to ignore. While the incident represents a setback, it reinforces the importance of resilience and adaptability in scientific exploration. The quest to understand what happened during the telescope's observations of Proxima b will undoubtedly continue, as will the search for habitable worlds and extraterrestrial life. Even if no definitive answers emerge from this incident, the intrigue it has generated will fuel further investigations, drive technological innovation, and inspire a new generation of scientists and explorers. Each challenge faced in space exploration brings lessons that inform the next phase of discovery, bringing humanity closer to answering age-old questions. Are we alone in the universe? And if not, what forms might our cosmic neighbors take? Another technological implication of the mysterious shutdown could be the development of more sophisticated onboard data processing and storage capabilities. With such high stakes in data collection, especially when investigating potential signs of extraterrestrial life, space observatories may need to employ advanced artificial intelligence systems. These systems could autonomously analyze and prioritize data, ensuring that even if communication with Earth is lost, valuable information is preserved. Such capabilities could transform space exploration, allowing missions to adapt dynamically to unforeseen challenges and ensuring that crucial data isn't lost. There's also a renewed call for distributed space telescope arrays. Instead of relying solely on a single large observatory, deploying constellations of smaller specialized telescopes is gaining traction. These arrays could be distributed across various orbits or even positioned at different points throughout the solar system to observe distant objects simultaneously from multiple perspectives. This approach would provide redundancy and a broader observational capacity, enabling simultaneous coverage of different wavelengths or multiple targets. If one instrument goes offline, the remaining components can continue the mission, reducing the risk of catastrophic data loss and enhancing our ability to detect subtle signals that might indicate life or unique planetary processes. The interest sparked by the blackout and its potential connection to Proxima b may also accelerate timelines for more ambitious space missions focused specifically on detecting life. Projects like the Breakthrough Starshot initiative, aiming to send tiny, light-propelled probes to the Alpha Centauri system, could receive increased funding and public support. By sending small, fast spacecraft equipped with cameras and instruments capable of gathering direct data, humanity could achieve unprecedented detail in studying exoplanets like Proxima b. The incident may prompt a re-evaluation of the kinds of exoplanetary signatures scientists prioritize in their search for life. Historically, the focus has been on finding Earth-like conditions, liquid water, a stable atmosphere, and an energy source. However, the strange atmospheric signals detected suggest life could exist in forms or under conditions not yet considered. This could broaden the criteria used to assess habitability, leading scientists to investigate more exotic biosignatures. For instance, certain gases or isotopic ratios that seem unrelated to biological activity might be re-examined for their potential as indirect indicators of life, especially in vastly different atmospheres. Another intriguing avenue is the concept of technosignatures, evidence of technology or industrial activity on other planets. Traditionally, the search for extraterrestrial intelligence has concentrated on detecting radio signals. But this approach may be too narrow. If signals from Proxima b were artificial, they might not manifest as conventional radio waves, but could involve different types of electromagnetic emissions, anomalous heat signatures, or unusual light patterns. This event might push researchers to develop new methods for detecting such signs, utilizing novel algorithms that sift through massive data sets to identify anomalies indicating technological artifacts or advanced life forms. While the investigation continues, the telescope's blackout has influenced how astronomers and astrobiologists think about the fragility and vulnerability of space missions. Future observatories may need better shielding against cosmic radiation and stellar flares, especially when observing volatile star systems. They may also require real-time adaptability to unexpected cosmic events. Adaptive shielding that dynamically responds to environmental changes in space could become standard, helping prevent disruptions by automatically adjusting to sudden spikes in radiation. As discussions about Proxima b's possible significance evolve, the incident prompts deeper theoretical inquiries into the nature of communication in the universe. If there were intentional interference by a higher intelligence, it raises fascinating questions about how different civilizations might communicate across interstellar distances. Would an advanced civilization choose to obscure its presence to avoid detection? Could the anomalies be a form of cosmic camouflage or an attempt to signal in a manner not yet understood by human science? These speculative but compelling questions encourage new paradigms in interstellar communication, broadening the scope beyond conventional radio and light-based signals to include more cryptic or indirect forms of interaction. Moreover, the implications of potentially encountering life or intelligent signals would extend far beyond science. Philosophical, cultural, and even theological considerations would come to the forefront, challenging humanity's understanding of its place in the cosmos. The discovery of life, especially intelligent life, on another planet would prompt profound questions about the uniqueness of human existence. Religions and cultural narratives may have to reconcile with the idea that life exists elsewhere, possibly with different forms of consciousness or societal organization. Such a revelation could unify humanity under a shared identity as Earthlings, fostering a greater sense of global collaboration and responsibility to preserve our planet, knowing that life isn't a solitary phenomenon in the universe. In philosophy, this incident could invigorate discussions about the nature of consciousness and its potential manifestations beyond Earth. If Proxima b hosts life, particularly intelligent life, it could challenge anthropocentric views of intelligence and consciousness. Philosophers and scientists might revisit theories of mind, awareness, and ethics, considering that consciousness could arise under vastly different conditions. The implications could extend to the ethical treatment of hypothetical extraterrestrial life, raising questions about rights, responsibilities, and protocols for contact. The telescope's sudden blackout has also highlighted the psychological aspects of space exploration. The public's response reflects a deep-seated fascination with the search for life beyond Earth and a fear of the unknown. If life or advanced technology were found on Proxima b, it would challenge not only scientific, but also societal perceptions of what it means to be human. The event has stirred imaginations worldwide, fueling excitement and anxiety about the possibility of first contact. This psychological impact could shape public policy, influencing funding for space exploration and guiding international efforts toward collaborative approaches in handling discoveries that could reshape humanity's self-view. The mysterious nature of the blackout, paired with the anomalous data, has led to renewed interest in contingency planning for potentially disruptive space-based discoveries. There's already discussion about forming dedicated task forces or intergovernmental agencies to manage the implications of discovering extraterrestrial life or technology. Such groups would focus not only on scientific analysis, but also on addressing social, political, and economic ramifications. Policies might be crafted to establish protocols for data sharing, public announcements, and careful interpretation of findings to avoid misinformation or panic. Governments and space agencies could consider contact scenarios akin to disaster preparedness plans to ensure readiness for whatever lies out there. While the true cause of the communication failure is yet to be determined, the incident invites re-evaluation of how we interpret astronomical data, particularly when dealing with potential extraterrestrial phenomena. It has triggered conversations about the limitations of human cognition in processing novel forms of data. The possibility that our instruments encountered something our current scientific models can't explain highlights the importance of keeping an open mind. This openness must be tempered by rigorous scientific analysis to avoid premature conclusions. The search for life and intelligence in the universe is fraught with uncertainty, and the incident serves as a reminder that while we can make incredible advancements, the cosmos remains a place of mystery where answers aren't always immediate. In the absence of a definitive explanation, the mystery surrounding the telescope's blackout encourages speculative thinking about the universe's nature and our place within it. The questions raised aren't just about what we found or didn't find on Proxima b, but about the limits of our knowledge and the potential for future discoveries that could change human history. It challenges scientists to push beyond conventional boundaries in methods and theories, exploring the fringes of what's considered possible. Each new discovery, each anomaly, brings us one step closer to understanding the vast, complex universe we inhabit. Whether the telescope's silence was due to technical failure, cosmic interference, or something more extraordinary, it has undeniably reignited our collective curiosity and determination to seek answers. Since its launch in 2021, the James Webb Space Telescope has sparked a persistent question in the minds of the public. It's a question that ignores the wealth of data about ancient galaxies or the formation of stars and focuses on just one thing. When will the JWST find evidence of alien life? Surprisingly, this question isn't as far-fetched as it might seem. NASA has long prioritized the search for extraterrestrial life. Whether it's a microbial fossil buried in Mars's ancient lake beds or a simple organism in Europa's hidden ocean. However, while the Mars and Europa missions remain largely speculative, the JWST could be on a much faster track. It might even discover signs of alien life as early as next year. In September, researchers using the JWST made a potentially groundbreaking discovery in the atmosphere of the exoplanet K2-1b. They found promising indications of both water and a molecule that could be linked to life. With follow-up observations planned for 2024, we may be on the verge of a major breakthrough. However, as we will soon explore, many planetary scientists remain skeptical of these findings. A skepticism that touches on one of NASA's toughest modern challenges: how we can ever be certain that we've truly discovered alien life. Among the array of discoveries made by the JWST, this one stands out as particularly significant, possibly the most important to date. On September 12, 2023, a research team from the University of Cambridge, led by Professor Niku Madhusudan, released the results of their recent observations of K2-18b. This exoplanet, located about 120 light-years from Earth in the constellation Leo, has intrigued scientists since 2019, when the Hubble Space Telescope detected potential water vapor in its atmosphere. That initial finding prompted the Cambridge team to turn the powerful JWST towards K2-18b, though what they ultimately discovered exceeded all expectations. The findings revealed both methane and CO2 in K2-18b's atmosphere, along with an absence of ammonia. National Geographic explained that according to theoretical models, a large planet like K2-18b could only have that mix of gases if the atmosphere was interacting with water below. The possibility that K2-18b might be an ocean world, one covered by a sea far greater than anything on Earth, was already a thrilling prospect. However, Professor Madhusudan's research took it even further. In addition to methane and CO2, the JWST detected dimethyl sulfide, DMS, a molecule typically linked to life. As the Cambridge professor told the BBC, on Earth, DMS is only produced by life. Most of it in our atmosphere comes from phytoplankton in marine environments. While the team emphasized that the DMS detection was of low confidence and more observations are required, the notion of alien plankton was hard for many to ignore, and understandably so. NASA is currently engaged in a decades-long mission to discover non-terrestrial life. The Mars Sample Return mission alone is investing over $8 billion to retrieve material from the red planet in hopes of finding signs of ancient microbial life. Meanwhile, next year, the Europa Clipper, with a budget of $5 billion, will set off on its journey to Jupiter's water moon to investigate whether it could theoretically support living organisms. This is why the possibility of the JWST detecting a known biosignature in the atmosphere of an exoplanet is so captivating. Dreams that perhaps some were too eager to embrace. But we'll get into the reasons to be skeptical a bit later in this video. Right now, we need to cover a few crucial points for everything else to make sense. First, what exactly is K2-18b? And second, how do we even begin to detect anything in its atmosphere, given that it's such an incredibly distant planet? After all, it's really far away. To answer these questions, let's embark on a little journey through the cosmos, leaving Earth behind, gliding across the vast expanse of space until we arrive in a distant solar system about 120 light-years from home. This solar system is where one of the most fascinating exoplanets ever discovered resides. The straightforward answer to the question, what is K2-18b, is rather simple, though the finer details remain somewhat unclear. At its core, K2-18b is an exoplanet situated more than 120 light-years away, falling into the category known as sub-Neptunes. This means it is larger than Earth but smaller than Neptune. Specifically, it has a radius roughly 2.6 times that of Earth, a size range that does not exist in our solar system. This unique classification makes it challenging for scientists to theorize about what K2-18b might truly be like. For most rocky exoplanets, we expect them to be similar to Earth or Mars. When we look at distant gas giants, we anticipate that they will have something in common with Jupiter or Saturn. But sub-Neptunes? Well, there's nothing in our solar neighborhood to draw comparisons with. As the saying goes, scientists are fumbling in the dark, like a blind man at an orrery. We do, however, know enough about K2-18b to make some informed assumptions. For instance, we are aware that it orbits its parent star, a red dwarf referred to as K2-18 within the habitable zone. This means that if water were theoretically present on its surface, it would be in liquid form, similar to the conditions found on Earth. However, it doesn't orbit at the same distance from its star as Earth does from the Sun. While the distance between our Sun and Earth is 1 astronomical unit, AU, K2-18b is much closer to its star, at only 0.16 AU. In our solar system, that would be significantly nearer than Mercury. It is so close, in fact, that a year on K2-18b would last only 33 days. Its proximity is such that if it were orbiting our Sun, the intense heat would scorch its surface beyond recognition. Fortunately for any potential space plankton on K2-18b, its star is significantly cooler than our own. So cool, in fact, that the two could almost embrace without instantly turning any surface water into vapor. And this is a crucial detail because, according to recent theoretical studies, surface water might be a defining characteristic of planets like K2-18b. In 2021, Professor Niku Madhusudan, the very scientist whose team may have identified DMS, released a fascinating paper in the Astrophysical Journal about the makeup of sub-Neptunes. In its simplest form, his claim was that these planets might harbor an entirely new class of exoplanets, ones encased in massive oceans beneath hydrogen-rich atmospheres. He has since dubbed these planets Hycean worlds, a term blending hydrogen and ocean. If they exist, these water worlds could be completely unlike anything humanity has ever come across. With up to 10 times the mass of Earth and twice its radius, they would be intensely hot, reaching temperatures as high as 200 degrees. Even with this extreme heat, the main feature of these Hycean planets wouldn't be a barren, steamy void, but rather a vast layer of water surrounding a small rocky core. A colossal ocean that could make up as much as 90% of the planet's entire mass. This ocean, at least theoretically, might be capable of supporting basic microbial life. Moreover, the thick atmospheres on these worlds would offer a much wider zone of habitability around their parent stars compared to rocky planets like Earth. It's similar to how Canadians manage to walk around in t-shirts in temperatures that would leave most of us shivering. Given the large number of sub-Neptunes that we know exist, coupled with this broader habitable zone, Hycean worlds could be prime candidates for finding life, especially since larger planets are, as you would imagine, easier to observe from a distance. This is why Madhusudan's team decided to use the JWST to peer across the vast expanse of space at K2 and 18b, a move that might, just might, soon lead to confirmation of the existence of Hycean worlds. However, as we're about to explore, this is no simple task. Even with the immense capabilities of the JWST, detecting ocean worlds is extremely complicated. In January and again in April of 2023, the JWST focused on the star K2-18 for a total of 5 hours. These 5 hours were divided into 2 separate blocks, each lasting 2.5 hours. During this time, K2-18b crossed in front of its parent star, and as it did, the star's light passed through the planet's atmosphere. It was the light captured by the JWST that enabled Madhusudan's team to draw their conclusions about the atmospheric composition. As the BBC detailed, that light holds the chemical signature of the molecules within the atmosphere. By splitting the light into its component frequencies, much like how a prism creates a rainbow spectrum, the details can be deciphered. If certain parts of the spectrum are absent, it means they have been absorbed by specific chemicals in the planet's atmosphere, thus allowing researchers to determine its composition. This is the method we use to uncover which molecules exist on distant planets. However, it's far from a simple matter of glancing at the spectrum and exclaiming, "Oh, look, aliens!" Every detection comes with something scientists refer to as a sigma value. For the rest of us, a sigma value is essentially a measure of how confident researchers are that what they've detected isn't just a fluke or an embarrassing mistake. To give an example, if something is detected with a 1 sigma signal, it means there's a pretty decent chance the molecule you're looking at is as real as that high school girlfriend who supposedly lived in Canada. A 2 sigma signal is a bit more believable, like a guy bragging about how much weight he can lift. Plausible, but still maybe not entirely true. Once you reach 5 sigma, though, you're dealing with something that's almost certainly real, like the fact that I'm bald. At that point, disproving it would take some seriously strange circumstances. In general, the scientific community won't fully accept a discovery unless it hits at least a 3 sigma threshold. Anything below that is seen as too shaky to rely on. For K2-918b, the JWST detected methane in the atmosphere with a 5 sigma confidence level, meaning we can be virtually certain it exists. On the other hand, the detection of CO2 came in at a confidence level of 3 sigma. This is less certain, but still probably reliable enough to be accepted by the scientific community for the time being. However, one thing the JWST did not detect, with any meaningful confidence at all, was water vapor. The water vapor that Hubble had supposedly found back in 2019 turned out in the 2023 results to have been a false reading caused by methane instead. Madhusudan's team is excited about the possibility that this planet could be a Hycean world because the combination of molecules found in its atmosphere aligns with the theoretical model for such a world. However, this doesn't confirm the presence of an ocean. As JAXA's astrophysicist and science communicator Elizabeth Tasker put it in a blog post, "We have not discovered water on K2-18b. All we can say is that the planet does not have an ocean." If this kind of cautious language sounds frustrating, well, that's the reality of how science operates. While it would be fun to dive into the excitement of distant ocean worlds, our responsibility is to follow the approach taken by serious astrophysicists and remain cautious when discussing Hycean planets. This measured approach is especially critical for the most thrilling aspect, the possibility that the JWST has detected a molecule linked to life. Early next year, the JWST is expected to once again focus its powerful instruments on K2-18b. Over the course of the 2.5 hours that the planet transits in front of its star, Professor Madhusudan's team will attempt to strengthen confidence in some of their previous findings, seeking more solid proof that a global ocean truly exists, and once more trying to detect that life-signaling molecule, DMS. Webb's mid-infrared tools, which are specially designed to search for evidence of DMS, will assist in this effort. Given that confirming this could suggest the presence of alien organisms, there is naturally a great deal of excitement. However, this excitement will be tempered with extreme caution for one significant reason. The original DMS detection, which generated numerous articles, including this very video, was not very reliable. In fact, it had a sigma value of only 1, about as plausible as the infamous girlfriend from Canada. Excuse. As planetary scientist Joanna Barstow kindly explained to Chemistry World magazine, it is a very tentative detection. Still, even a low-confidence detection of something that might indicate extraterrestrial life deserves closer scrutiny. Proving the existence of space plankton would truly be one of the most extraordinary discoveries ever, demonstrating that life evolved independently from Earth at least once, implying it may have done so dozens or even hundreds of other times throughout the universe. Unfortunately, though, even if the JWST delivers a 5 sigma value detection of DMS next year, we still can't just jump up and shout, "Woo, space creatures, yay!" First, scientists would need to eliminate any possible natural, non-living explanations for the molecule's presence. While DMS on Earth is indeed linked only to life forms, that might not hold true on K2-18b. The key reason? Hycean worlds, if they exist, would be so fundamentally different from anything we've ever seen that we can't make any assumptions. When someone like our channel pops up on your YouTube talking about ocean worlds, you're probably thinking, "Oh, cool, just like that Kevin Costner movie." In that case, you're likely picturing a planet similar to Earth, just minus all the land. But in reality, Hycean worlds are much stranger than that. Astrophysicist Ethan Siegel wrote an insightful article on Big Think that explains the difference. In his analysis, any planet with over twice the mass of Earth and a radius exceeding 1.3 times that of our planet cannot be a rocky world like Earth. Moreover, any planet with a radius greater than 1.75 times that of Earth ends up resembling Neptune far more than it does our homeworld. Neptune, in fact, is an extraordinary place, an intriguing world where diamonds rain down and atmospheric pressures reach levels so high that NASA has described it as creating a hot, dense fluid of icy materials and an ocean of superheated water. This Neptunian ocean exists far beyond normal boiling points, but remains liquid due to the immense pressure. However, it is completely uninhabitable, a brutal landscape that would obliterate any known form of life faster than a game of beer pong played with cyanide. If K2-18b has an ocean, it could very well be something similar. Siegel discusses planets of similar size, stating that if a hydrogen-helium atmosphere constitutes even 0.5% of the planet's total mass, the surface pressure will be tens of thousands of times greater than what we experience on Earth, with temperatures soaring into the thousands of degrees. This means K2-18b cannot be an ocean-covered world akin to Earth. And therein lies a major issue. If K2-18b is so vastly different from Earth, we cannot automatically assume that an Earth-based biosignature, like DMS, similarly indicates Earth-like life on this distant exoplanet. To quote Elizabeth Tasker once again, we need a lot more information about conditions on that planet to be sure that a biosignature on Earth could not be abiotically created in a different environment. Such studies have not yet been done for K2-18b or Hycean worlds in general. That quote concludes, "Now it's clear that a great way to advance such studies would be for someone to confirm the presence of DMS in K2-18b's atmosphere. Therefore, the JWST searching for it next year remains an incredibly exciting endeavor. However, it also implies that the likelihood of detecting alien life may be further off than we initially hoped, particularly when considering all the other potential issues associated with Hycean planets. Let's go back to September 2020, during the height of the pandemic, when the monotony was interrupted by a rather spectacular news event. As the world was in the grips of lockdown, a team of scientists reported detecting a molecule in Venus's upper atmosphere, one that was thought to signal life. What followed was a massive media frenzy, with many declaring that we might have discovered Venusian space organisms. Even today, some still believe NASA's selection of 2 Venus probes for its next discovery mission, announced shortly after, was influenced by the phosphine discovery. Fast forward to 2023 and the consensus among scientists is clear. We don't have solid evidence of phosphine in Venus's atmosphere. While it might still be present, the 2020 findings were far from robust enough to justify the high-profile announcements that followed. This is a key reason why caution is being exercised around DMS on K2118b. However, other factors contribute as well, including significant theoretical challenges with Hycean planets. One major issue is the likelihood of runaway greenhouse effects. Due to the high levels of hydrogen in their atmospheres, Hycean worlds would interact with sunlight in ways that are vastly different from Earth. Recent studies have demonstrated that if such a planet had Earth-like atmospheric pressure and orbited at a similar distance from its star, its oceans would quickly overheat and evaporate. To maintain liquid water, a Hycean planet would need to orbit much farther from its star, beyond Mars, past Ceres, and all the way past the asteroid belt's edge. Only at around 385 AU could a typical Hycean world, with atmospheric pressures 10 times that of Earth, manage to retain an ocean. The main issue, we haven't identified any Hycean world candidates within this new, extended habitable zone. That includes K218b. Even though its star is significantly cooler, the planet is likely still too close to support liquid water. And even if an ocean were confirmed, that wouldn't guarantee the presence of life. In fact, the planet might not be habitable at all, largely due to the immense pressure created by the sheer mass of water in a global ocean. To quote expert Elizabeth Tasker once more, "A vast global ocean exerts such immense pressure on the planet that it suppresses the geological activity forming under high-pressure conditions. Deep sea ice would form and effectively seal off the rocky layers of the planet, thereby, at a minimum, halting the carbon silicate cycle. If the carbon silicate cycle stops, then other mechanisms must step in to regulate greenhouse gases, maintaining a habitable temperature and delivering the necessary nutrients typically sourced from silicate rocks. Without these nutrients, life forms would have nothing to sustain them, nothing to spark the chemical processes essential for life to emerge. Although it's possible, in theory, that meteorites could introduce sufficient nutrients into the ocean, it's equally possible that Hycean planets, if they exist, are simply barren water worlds. We won't really know until we get to observe one up close and truly understand what's going on there. All of which is our very long and drawn-out way of explaining that while the detection of DMS on a water-covered exoplanet is undeniably exciting, it's unlikely to confirm the existence of extraterrestrial life, at least not anytime soon, and certainly not without a significant amount of additional research. And honestly, this isn't the outcome we were hoping to share with you when we began working on this video. We'd much rather be here saying that we're about to uncover the scientific proof of bizarre space creatures. But as the saying goes, extraordinary claims require extraordinary evidence. And as we've shown, the presence of DMS alone may not be enough to support that claim. However, this doesn't mean we have to end this video on a negative note. Whether or not aliens are involved, the exploration of K208b remains incredibly fascinating. Thanks to the JWST, we are now, for the very first time, beginning to understand the different types of planets that exist in our universe. Giant worlds far larger than Earth are waiting to be explored. Planets whose mysteries we are gradually uncovering, one observation after another. These worlds could ultimately prove to be uninhabitable nightmares. Or perhaps the Hycean worlds theory is correct, and we're actually surrounded by a multitude of thriving oceanic planets. The key takeaway here is that we won't know for sure without carefully studying these distant realms. Whether or not signs of life are eventually found, Professor Madhusudan's team is performing a crucial service by starting to break down these cosmic mysteries. In doing so, they open the door to the possibility that in the near future, another scientist will take a reading with the JWST and indeed find a biosignature, finally announcing to the world, yes, it's aliens. We can only hope that day comes sooner rather than later. We hope you enjoyed this journey through space, and if you did so, we would really appreciate you hitting the like button. For more content like this, feel free to subscribe to A World to Discover. While you're still here, go ahead and watch more from our channel by clicking the videos on your screen right now. As telescopes like the James Webb peer into the Milky Way, you've likely come across the growing excitement about newly discovered exoplanets. Remarkably, it was only in 1992 that we detected the first planet outside our solar system. Yet since then, more than 5,500 have been confirmed within the small region of space we occupy, stretching just a few thousand light years. Considering the Milky Way spans 105,700 light years in diameter, this discovery suggests the thrilling possibility of billions, if not trillions, more planets scattered throughout our galaxy. On average, each star likely has at least one planet, if not several. With all these exoplanets out there just waiting to be discovered, it's only natural that our attention would shift towards Goldilocks zones and the idea of planet habitability. After all, humanity is setting its sights on colonizing the stars, and, mathematically speaking, an Earth 2.0 is surely out there waiting for us. In fact, you've probably already encountered the term Earth 2.0 in the headlines of various articles or videos claiming that a new planet has been found that could be the perfect candidate for human life and future colonization. The excitement surrounding these discoveries fuels our imagination, making the idea of finding another Earth seem not only possible, but perhaps inevitable. However, don't believe the hype. Despite all the excitement surrounding these discoveries, the truth is that every planet we found so far has, putting it bluntly, sucked. None of them come close to being ideal for human life. In fact, once you hear the details about these planets, you'll quickly realize why moving to any of them would be the absolute last thing any sane person would ever want to do. The reality of their extreme conditions makes the idea of living there more of a nightmare than a dream. Join us today for a grand tour of the potential Earth 2.0s that have been discovered, as we explore these intriguing candidates for humanity's future home. We'll also break down why this may not be the ideal time to invest in the planetary property market just yet. When choosing an Earth 2.0, much like buying a house, it's crucial to begin by identifying your non-negotiables. Some of these factors are relatively straightforward to think about. For example, temperature. You want a comfortable, temperate climate somewhere that's neither too warm nor too cold. Since temperature decreases the farther a planet is from its star, every planetary system has a sweet spot where the temperature of a planet is likely just right, not scorching hot and not freezing cold. This idea mirrors the classic Goldilocks story, where she found her perfect bowl of porridge, neither too hot nor too cold. As a basic guideline, if a planet is located at the right distance from its star, it could very well have a suitable temperature for us to consider calling it home. Of course, this is by no means a guarantee. Venus, for example, a planet located within this zone, should theoretically be ideal for life. However, its thick, toxic atmosphere makes it the hottest planet in our solar system, even though it's farther from the Sun than Mercury. This shows that atmosphere is a crucial factor in determining a planet's habitability. When considering Earth 2.0, atmosphere is key. Ideally, you'd want one with oxygen and water vapor, and nothing that could harm us. At the very least, it should be capable of trapping heat and providing some protection from space radiation. However, an important factor to consider is the neighbors nearby. One major reason why many exoplanets in our galaxy don't meet the mark is due to the stars they orbit. Our own star, the Sun, is classified as a G-type yellow dwarf, a relatively fast-burning, short-lived type of star, especially when compared to other stars in the universe. Stars like our Sun typically live for about 10 billion years before their cores begin to collapse, eventually transforming into red giants. This stability, while short in cosmic terms, has been essential for life to flourish here on Earth. Yet yellow dwarfs like our Sun are actually quite rare in the Milky Way, making up only about 10% of the galaxy's total star population. In contrast, red dwarfs are far more common, comprising around 75% of all stars. These stars have extraordinarily long lifespans, often surviving for up to 14 trillion years, which is longer than the universe itself has existed. However, despite their longevity, planets orbiting red dwarfs face a host of challenges, as these stars come with significant drawbacks that can complicate the development of life. For starters, red dwarfs have a much closer Goldilocks zone compared to their yellow cousins. Since they burn far less brightly, with luminosities ranging from just 10% to a mere 0.0125% of our sun's, the habitable zone, or Goldilocks zone, lies significantly closer to the star. This means that unless you're okay with living on a planet cloaked in what would feel like eternal night, which frankly sounds cold and pretty depressing, not to mention the difficulties it would pose for growing plants, you'd want an Earth 2.0 to orbit much nearer to its red dwarf to compensate for the lower light levels. Being closer would allow the planet to receive enough heat and light to support life, making it possible for plants and ecosystems to thrive in what might otherwise be a dim and chilly environment. This wouldn't be an issue on its own, if not for the second characteristic of red dwarfs that makes them such unpleasant neighbors: their instability. Our sun is the primary driver of space weather, constantly sending out streams of solar winds, flares, and coronal mass ejections. These phenomena can be intense, but they pale in comparison to the space weather generated by red dwarf stars. Flares from red dwarfs can be anywhere from 100 to 1,000 times more powerful than those from our sun. The frequent outbursts of plasma and radiation are so intense that they can strip away a planet's atmosphere and even cause any liquid water in the habitable zone to boil away. In red dwarf systems, planets are typically much closer to their star, making the odds of life developing quite slim, as the constant bombardment of deadly X-rays can wipe out any potential for life before it has a chance to arise. If humans were ever to consider living on a planet around a red dwarf, they would need far more than just some strong sun cream to survive. This rules out many exoplanets, such as the astronomers' favorite Kepler 186f, which some scientists once hoped might be habitable. While it could theoretically be possible to survive for a while in quite uncomfortable conditions, perhaps in a deep underground bunker on such a planet, the experience would be far from pleasant or sustainable in the long term. Even during calmer periods between harsh solar weather events, there's still another significant issue with planets that orbit red dwarfs: their strong tendency to become tidally locked. This means one side of the planet always faces the star, while the other remains in perpetual darkness, creating extreme conditions that make the planet even less conducive to human life. Being tidally locked means that the same side of the planet always faces its star throughout its orbit, creating a situation where one hemisphere experiences perpetual daylight while the other is locked in eternal darkness. This lack of rotation between day and night results in extreme conditions, with one side of the planet enduring relentless heat and the other plunged into freezing cold. The side facing the star could become a barren desert scorched by the constant heat, while the dark side would be perpetually frozen, covered in ice. Planets near their stars are more prone to becoming tidally locked due to gravitational forces. Mercury, for example, has incredibly long days that span 176 Earth days, or 2 Mercurian years. This absence of rotation makes it difficult for the planet to sustain life, as the temperature extremes on both sides would render much of the surface inhospitable for habitation. Even if humans attempted to survive in the narrow band of twilight that rings a tidally locked planet, the availability of liquid water would likely be a significant challenge. Any moisture present in the air that drifted toward the planet's dark side would freeze, becoming trapped as ice and essentially lost. As a result, the planet as a whole would be extremely dry, with very little chance of moisture circulating back to areas where it might be useful. Even within the twilight zone, which might offer more moderate temperatures, there would be no rainfall to replenish water supplies, making the environment harsh and unwelcoming for sustaining life. And that's not to mention the weak magnetic field likely to be found on a tidally locked planet. The dynamo effect, which powers Earth's magnetic field, is believed to be largely driven by the Coriolis effect. the planet's rotation generating momentum within the rising and falling liquid metal in its core. This movement helps sustain Earth's strong magnetic field, which shields us from solar radiation. On a tidally locked planet, where one side always faces its star and rotation is minimal or non-existent, this critical process would be significantly reduced or even absent, leading to a much weaker magnetic field and, consequently, less protection from cosmic and solar radiation. So, we're sorry to say that this rules out planets such as Proxima Centauri b, our closest exoplanet. Proxima Centauri b is otherwise an intriguing candidate. Its proximity makes it one of the most accessible planets for exploration, being situated just 4.2 light-years away from us. This distance makes it relatively close in cosmic terms, and its rocky composition adds to its appeal, especially since living on a gas giant could prove difficult for those of us who prefer solid ground beneath our feet. Even more compelling is the fact that its mass and radius closely mirror those of Earth, suggesting that its gravitational pull would be quite similar to what we experience here, potentially offering a familiar environment in terms of weight and movement. Why is this important? Let's compare it with another Earth 2.0 contender, Kepler 452b. This was the first planet to ever earn the title and was even described by a NASA scientist as the closest twin to Earth. Kepler 452b has a lot going for it. It orbits a yellow dwarf star, just like Earth, and it's at a similar distance, placing it within the so-called Goldilocks zone, where liquid water could potentially exist on its surface. However, there's a catch. It's classified as a super-Earth. This means that while it shares many similarities with our planet, its mass and radius create a gravitational force about twice as strong as Earth's. This stronger gravity could pose significant challenges for humans and other forms of life as we know them, affecting movement, growth, and overall livability despite its promising location. When it comes to gravity, how much is too much? Some scientists researching this question suggest that humans could potentially survive up to 4 times Earth's gravity, though this is considered the upper limit of what our bodies could endure. Even living in just twice Earth's gravity, however, could prove to be extremely uncomfortable and taxing. To visualize what this might feel like, imagine lying down and having a second person lie directly on top of you, pressing all of their weight against you. This would be your nightly routine, struggling for every breath under the pressure. Then, when morning comes, you would have to not only get out of bed, but lift that extra weight with you, strapping it to your back and carrying it with you throughout the day. Every step would be harder, every task more exhausting, and you'd be constantly aware of how fragile your body has become. A simple fall could easily result in broken bones, and tumbling down a flight of stairs would not just be painful, it could be deadly. Everyone would have to endure this. The elderly, struggling with frailty, the sick and infirm, already burdened by their own bodies, even small infants taking their first unsteady steps. Keeping this in mind, it's easy to grasp just how exhausting life in double gravity might end up being, as every simple movement would become a monumental effort. If you're a bodybuilder or an athlete, your well-conditioned muscles and stamina might allow you to cope better, but even then, the constant strain would take its toll. For most people on Earth, however, it would feel like a slow, unrelenting torture. Your heart would be working overtime, pounding furiously in an attempt to circulate blood efficiently, and the sheer effort of standing upright would make it feel like you're running a race, even when you're doing nothing more than staying still. And if you were to triple the gravity, it would be like carrying 2 additional people on your back at all times, and things don't get much better going the other way. Sure, everything suddenly feels easier as the weight is lifted, but living under reduced gravity brings a whole new set of health risks. We can already see this from astronauts who've spent just a few months aboard the International Space Station. Over time, the calcium in your bones begins to bleed out, making them brittle and more prone to fractures. Your muscles weaken and atrophy as they no longer need to support your body weight. Even your heart, no longer working as hard to pump blood, can develop complications, and your immune system becomes compromised. All in all, even with a rigorous daily exercise routine, your long-term prospects in a low-gravity environment aren't promising. This harsh reality poses a significant challenge for NASA scientists as they work to figure out how to establish human outposts on the Moon or Mars, where astronauts might live for several years and face these very dangers. Humans have spent millions of years adapting to life on our planet, shaping every aspect of our biology and behavior to fit Earth's unique environment. We've become deeply accustomed to the specific conditions here, from the air we breathe to the gravity we experience and everything in between. We're just not suited to life anywhere else. Our bodies simply haven't evolved to cope with the vastly different conditions that other planets or environments would present. In some ways, this is a remarkable testament to how well we've acclimatized to the particular balance of elements, climate, and atmosphere that Earth offers. It reflects the incredible adaptability that has allowed us to thrive here. But it also presents a significant challenge if we ever hope to live beyond Earth. The very adaptations that have allowed us to flourish on our home planet become limitations when faced with the prospect of living in worlds that don't share the same characteristics. And so, the hunt for Earth 2.0 goes on. As I mentioned, there are likely billions of undiscovered planets in our Milky Way galaxy. The odds of at least one being out there that meets our criteria for gravity, temperature, lack of life-threatening radiation, and the presence of atmosphere and water are high enough to be a certainty. However, actually finding one that meets all these criteria is a much more challenging task, especially considering that most planets remain invisible to even our most powerful telescopes. We can only detect them for a brief moment when they pass in front of a convenient star and block out its light. So if someone tells you that they've already found Earth 2.0, I'd take that claim with a pinch of salt. The reality is that we won't ever truly know if a planet is suitable for human life until we somehow bridge the vast gulf of space and physically explore it ourselves. Naturally, until we figure out how to achieve that, it remains somewhat of a pointless question for now. We truly hope you enjoyed this journey through space. If you did, please show your support by liking the video and subscribing to our channel. While you're still here, feel free to click on any of the other videos on your screen and continue exploring with us. Apollo 11's mission to the Moon on July 20th, 1969 was one of the most significant events in human history.
To achieving the goal, before this decade is out, of landing a man on the Moon and returning him safely to the Earth.
Astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface.
It's one small step for man, one giant leap for mankind.
While Michael Collins orbited above in the command module. This achievement symbolized human ingenuity and determination. However, Buzz Aldrin has long intrigued the public with his comments about the Moon. Over the years, he has hinted that the Moon may not be exactly what we think, sparking curiosity and speculation about its mysteries. Aldrin's views on the Moon often venture into the unusual. The second man to walk on the lunar surface, Aldrin has openly discussed his experiences during the mission. While most see the Moon as a barren, lifeless satellite, Aldrin has implied there's more to it. His reflections range from personal experiences to broader thoughts on what the Moon might represent for humanity, challenging the conventional view of the Moon as a cold, rocky body and suggesting that its mysteries are far from fully uncovered. During the Apollo 11 mission, Aldrin and Armstrong conducted experiments and collected samples to bring back to Earth. However, Aldrin has hinted in interviews that their time on the Moon may have revealed phenomena not fully disclosed to the public. Though his comments are often vague, they suggest the Moon could harbor unknown phenomena, leaving room for speculation and imagination about what was truly observed during the first lunar landing. Aldrin often emphasizes the sense of awe and mystery he felt on the Moon, describing it as an otherworldly place. His experience seemed to go beyond the typical overview effect astronauts describe, implying the Moon may hold deeper meaning or secrets. His reflections evoke a mystical quality to the lunar surface, defying simple scientific explanation. Aldrin's comments also raise broader questions about humanity's place in the universe. For millennia, the Moon has inspired mythologies, religious beliefs, and scientific inquiry. Aldrin suggests that the moon's significance might extend beyond its role as Earth's satellite, hinting at mysteries yet to be understood, potentially reshaping our understanding of the cosmos and our role in it. This resonates with the idea that the moon symbolizes the unknown, a reminder of the mysteries still beyond human comprehension. One intriguing aspect of Aldrin's perspective on the moon is what might lie beneath its surface. While the Apollo missions, including Apollo 11, provided valuable data, much of the moon's interior remains a mystery. Some scientists believe the moon could reveal clues about the solar system's formation, and Aldrin's musings suggest it may hold more than geological secrets, perhaps hidden structures, ancient artifacts, or other unknown phenomena. Aldrin has also fueled speculation about extraterrestrial activity. He once mentioned seeing an unusual object during the Apollo 11 mission, later clarifying it was likely part of the rocket, but the incident added to the mission's mystique. The moon's unique position in Earth's orbit, being unusually large and nearly perfectly circular, has led some to theorize it might be an artificial object created by an advanced civilization. While Aldrin hasn't endorsed this idea, his open-mindedness toward the moon's mysteries leaves room for speculation. Aldrin sees the moon as a crucial stepping stone for future space exploration. He has long advocated for continued lunar exploration and using the moon as a base for missions to Mars and beyond. Aldrin believes humanity's future lies in space, and establishing a permanent presence on the moon is essential, not just for scientific reasons, but also as preparation for further space travel. To him, the moon is both a mystery to solve and a gateway to the broader cosmos. Aldrin's respect for the unknown drives his curiosity about the moon, believing much remains undiscovered. He encourages humanity to keep exploring and questioning what we know, aligning with the spirit of pushing the boundaries of space exploration. For him, the moon is the frontier where humanity might confront the unknown and uncover extraordinary discoveries. Recently, Aldrin has stressed the need for renewed space exploration, especially as Earth faces global challenges. He believes the moon could help address these issues by serving as a platform for scientific research, resource extraction, and even habitation. His reflections on the moon's mysteries suggest that some of the answers to pressing human challenges may lie not on Earth, but on the moon and beyond. The implications of Aldrin's views on the moon are profound. If the moon is more than just a barren rock, as Aldrin implies, it could reshape our understanding of the universe and our place in it. The possibility that the moon holds hidden secrets, whether ancient artifacts, unknown geological formations, or signs of extraterrestrial activity, challenges the conventional narrative of space exploration and raises questions about what we truly know about our closest celestial neighbor. Aldrin's reflections encourage a re-evaluation of humanity's relationship with space. While space exploration has traditionally been driven by scientific curiosity, technology, and geopolitical competition, Aldrin suggests deeper philosophical reasons to continue exploring. The moon, in his view, symbolizes the unknown and reminds us that mysteries in the universe remain to be uncovered. This perspective calls for a more holistic approach to space exploration, considering not just the scientific and technological aspects, but also the broader implications for humanity's future. As NASA's Artemis program aims to establish a sustainable presence on the moon, Aldrin's reflections gain more significance. This new era of lunar exploration could provide answers to some of Aldrin's questions and reveal new mysteries. The possibility that the moon holds more than we previously thought adds excitement and intrigue to upcoming missions. It also reminds us that despite technological advancements in space exploration, profound questions about the universe remain unanswered. Aldrin's fascination with the moon stems from his first-hand experience of walking on its surface, which significantly shaped his worldview and led him to question established understandings of our natural satellite. While most focus on the triumph of Apollo 11, Aldrin's reflections emphasize the strangeness and mystery of the experience. His perspective suggests the moon may hold more significance than we realize, challenging our knowledge and inviting deeper exploration. Aldrin's insights indicate the moon may not be just a barren, lifeless rock, but something much more enigmatic. Aldrin's comments often suggest that the moon could be a key to understanding deeper cosmic mysteries, possibly linked to our understanding of space, time, and the origins of life. One major question raised by Aldrin's reflections is the moon's origin. While the prevailing theory is that the moon formed from debris after a giant impact between Earth and another planetary body, some aspects of its composition and behavior remain unexplained. For example, certain elements on the moon's surface do not fit neatly into this hypothesis, leading Aldrin to speculate that unknown processes may have influenced its formation. Aldrin has also expressed intrigue over the moon's gravitational relationship with Earth. While its role in stabilizing Earth's axial tilt in controlling tides is well known, Aldrin has suggested that this relationship might be more complex than we currently understand. The moon's orbit and its influence on Earth raise questions about whether an unknown force may govern these interactions, inviting further exploration of how celestial bodies affect one another in ways that might still be unexplored. Aldrin's interest in the moon is strongly connected to his curiosity about extraterrestrial life. While he has never claimed to have seen aliens or found direct evidence of their existence, his open-mindedness about space's mysteries often leads to speculation. The moon, being Earth's closest celestial body, is seen as a potential starting point for discovering life beyond our planet. Aldrin has suggested that if extraterrestrial life exists, it might have left traces on the moon, such as artifacts or subtle signs not easily detected. This makes the moon a significant target for future exploration. Aldrin's reflections also show his willingness to consider unconventional ideas, including the possibility that advanced civilizations visited the moon long before humans. Though speculative and lacking evidence, his open-mindedness encourages exploration of these ideas to deepen our understanding of the moon's history. Aldrin has speculated that the moon could serve as a hub for future human expansion into space. He has long advocated for permanent lunar bases to support missions to Mars and beyond, making the moon a critical stepping stone for humanity's future in space. His reflections weave together two ideas. The moon holds unexplored mysteries, and it plays a vital role in humanity's continued exploration of the cosmos. Aldrin's Apollo 11 experience instilled in him a sense of wonder and humility, seeing the moon as a symbol of the unknown, urging humanity to push the boundaries of knowledge and capabilities. A recurring theme in Aldrin's reflections is the potential for life beyond Earth. While the moon is unlikely to harbor life, its proximity to Earth and role in space exploration make it a key location for studying conditions that could support life elsewhere. Aldrin has suggested that the moon could be a laboratory for experiments to help understand the origins of life on Earth and other planets. Studying the moon's geology and solar interactions could offer clues about life's emergence in the universe. Aldrin is also interested in the moon as a platform for studying Earth and the cosmos. Its lack of atmosphere and stable position make it ideal for astronomical observations. He has advocated for building lunar observatories to study the universe in ways not possible from Earth, highlighting the moon's potential to unlock the mysteries of the universe. The idea of the moon serving as a base for human activity raises important questions about resource utilization. Aldrin has often discussed the potential for mining the moon's resources, particularly helium-3, a rare isotope that could be used for future energy production. Although this presents significant technical and ethical challenges, the possibility of supporting human exploration and development in space has intrigued Aldrin for decades. He emphasizes the need for careful planning and international cooperation to use these resources responsibly and sustainably. Aldrin is also optimistic about humanity's future in space. He believes that while space exploration poses challenges, they are not insurmountable. His Apollo 11 experience instilled in him confidence in human ingenuity and perseverance. For Aldrin, the moon is both a challenge and an opportunity, a place where humanity can test its limits and move forward into new frontiers. His reflections often emphasize that the moon, while mysterious and sometimes daunting, symbolizes hope and humanity's potential for great achievements. Beyond its scientific and exploratory significance, Aldrin has suggested the moon could help foster global unity. The Apollo 11 mission was a triumph for all humanity, not just the United States. Aldrin frequently speaks of the awe and wonder people worldwide experience watching humans set foot on another world. He believes future lunar missions could unite nations in pursuit of common goals, making the moon not just a scientific frontier, but a place where humanity collaborates toward a shared future. Aldrin's reflections emphasize the importance of preserving the moon's environment. Though a strong advocate for human exploration and development, he stresses the need for careful stewardship of the moon's fragile ecosystem. Its barren surface holds vital clues about the solar system's history, and Aldrin warns against damaging or disrupting this natural environment. His views highlight the balance between exploration and preservation, a critical theme as humanity's presence in space grows. Aldrin also believes the moon could serve as a training ground for future spacefarers. Its harsh conditions, low gravity, lack of atmosphere, and extreme temperatures provide an ideal environment for astronauts to develop skills and technologies for missions to Mars and beyond. He advocates for lunar training facilities, aligning with his vision of using the moon as a stepping stone for further exploration. Additionally, Aldrin sees potential in space tourism and commercial ventures on the moon. With companies like SpaceX and Blue Origin advancing space travel, he envisions partnerships between governments and private industry, making the moon a destination for tourists as well as scientific exploration. This idea builds on the growing trend of space commercialization, where private companies are increasingly taking on roles traditionally held by government space agencies. Aldrin envisions a future where private enterprise plays a key role in making the moon accessible, creating new opportunities for economic development and human experience. Beyond tourism, Aldrin sees the moon as a platform for advancing space-based manufacturing and technology development. The moon's low gravity and lack of atmosphere offer unique conditions for testing technologies such as space habitats, energy production, and resource extraction. He has emphasized the moon's potential as a testing ground for technologies critical to future Mars missions, including advancements in life support systems, radiation shielding, and habitat construction, all of which could be refined on the moon before being used for longer missions to Mars or beyond. Aldrin's interest in technology focuses on the long-term sustainability of human activities on the moon, particularly through renewable energy sources like solar power. The moon's lack of atmosphere and extended sunlight make it ideal for generating solar energy, which could power lunar bases and support human habitation. Aldrin has suggested that lunar solar power could also meet Earth's energy needs, transmitting energy back to Earth via microwave or laser beams. This concept, though early in development, could help address global energy demands and reduce reliance on fossil fuels. He also believes the moon's resources, such as helium-3 for fusion energy, could play a crucial role in solving challenges like climate change and resource depletion. While fusion energy technology is still being developed, Aldrin sees the moon playing a key role in providing clean, sustainable energy for future generations. His reflections also emphasize the importance of international cooperation in the exploration and utilization of lunar resources, stressing that the moon belongs to all humanity. Aldrin advocates for international frameworks to ensure responsible use of space resources, similar to the treaties governing Antarctica, to prevent conflicts and ensure equitable sharing of benefits. He frequently highlights the idea of space as a global commons and views space exploration as a shared human endeavor that transcends borders and political divisions. This perspective is especially relevant as more countries and private entities join space exploration. Aldrin advocates for international cooperation, believing that the challenges of exploring and using the moon and other celestial bodies are too vast for any one nation or organization to handle alone. He envisions countries working together, sharing knowledge, resources, and expertise to benefit all of humanity. Aldrin also emphasizes long-term thinking over short-term, politically driven decisions. For him, the moon offers a chance to lay a foundation for future exploration that will benefit both current and future generations of astronauts and spacefarers. He believes today's decisions on how we explore and use the moon will significantly impact humanity's future in space. Therefore, he supports a long-term, strategic approach prioritizing sustainability, cooperation, and responsible resource use. Aldrin's focus on long-term thinking ties closely to his belief in inspiring the next generation of scientists, engineers, and explorers. Throughout his career, Aldrin has passionately advocated for STEM education, often emphasizing the need to inspire young people to pursue careers in science and space exploration. He sees the moon, with its mysteries and potential, as a unique opportunity to capture the imagination of future generations. By pushing the boundaries of our knowledge and continuing to explore the moon, Aldrin hopes to inspire young people to dream big and contribute to advancing human knowledge and exploration. Aldrin's reflections on the moon also carry a spiritual dimension, often overlooked in discussions of space exploration. Though a man of science, Aldrin has acknowledged the profound awe that comes with seeing the universe from space. He often describes walking on the moon as both a scientific and deeply spiritual experience. For Aldrin, the moon symbolizes our connection to something larger, a reminder of the vastness of the universe and our small yet significant place within it. This sense of wonder is central to his reflections, underscoring that exploring celestial bodies isn't just about data or resources, but expanding our understanding of the universe and ourselves. This spiritual aspect also informs Aldrin's views on the ethical responsibilities of space exploration. He emphasizes the need for humility and respect, recognizing that we are venturing into parts of the cosmos we don't yet fully understand. Aldrin believes that as we explore the moon and beyond, we must act as stewards of the universe, avoiding harm to the environments we encounter or exploitation of resources that could negatively impact future generations. This view reflects a deep respect for the unknown and the potential for space exploration to reshape our understanding of the universe and ourselves. Aldrin's thoughts on the moon intersect with his broader interest in human evolution and survival. He has spoken frequently about humanity's need to expand beyond Earth to ensure long-term survival. For Aldrin, the moon is the first step, a place to develop the technologies and skills needed to thrive in space. The challenges of space exploration, he believes, will push humanity to evolve, both technologically and in understanding what it means to be human. Thus, the moon is not just a destination, but a catalyst for human evolution, testing our limits and preparing us for the next phase of cosmic exploration. Aldrin's vision of the moon as a stepping stone is also tied to his interest in space colonization. He advocates for permanent human settlements on the moon as a way to ensure humanity's continued presence in space. These settlements, he believes, could serve as bases for future missions to Mars and beyond, providing the infrastructure necessary for long-duration space travel. Aldrin's vision of lunar colonization isn't just about survival, though. It's also about expanding human civilization into new frontiers. He envisions a future where humans live and work on the moon, creating societies that reflect the diversity and creativity of humanity. In addition to colonization, Aldrin believes the moon could play a key role in scientific discovery. He frequently speaks of its potential as a base for studying the cosmos, conducting experiments, and pushing the limits of human knowledge. The moon's unique environment, lacking an atmosphere and close to Earth, makes it ideal for scientific research, particularly in astronomy, geology, and biology. Aldrin envisions the moon becoming a hub for global scientific discovery, drawing researchers from around the world to unlock the universe's secrets. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us what surprises you expect from this reveal. We want to hear from you. Thanks for watching, and see you next time. The night sky is on the brink of a dramatic transformation as Antares, a red supergiant star 700 times larger than our Sun, approaches the end of its life and teeters on the verge of a supernova. Its impending explosion could outshine even Betelgeuse and rival the luminosity of our entire galaxy. As we anticipate this cosmic event, one pressing question remains. What will occur when this stellar giant finally erupts? Imagine gazing at the horizon and witnessing a sunrise that fills the entire sky. That would be terrifying if caused by a supernova. First off, a supernova is an exploding star and ranks among the most massive releases of radiant energy in the entire universe. Betelgeuse is a red giant star. If placed where our Sun is, it would extend out to the orbit of Jupiter. It's enormous, highly unstable, and on the brink of explosion. Observable supernovae within our galaxy are exceedingly rare. The last recorded instance happened centuries ago, making the potential explosion of Antares a once-in-a-lifetime spectacle. This upcoming celestial display offers astronomers and space enthusiasts a unique chance to witness cosmic history unfold before their very eyes. As we embark on this journey through the cosmos, we'll delve into the far-reaching impacts of this stellar explosion, from the creation of heavy elements to the potential formation of neutron stars or black holes. The aftermath of Antares supernova will shape the fabric of our galaxy for eons to come. Join us as we unravel the mysteries surrounding this cosmic ticking time bomb and its profound implications for our understanding of the universe. Antares, the red giant's final act. In the vast expanse of our night sky, one star stands out as a true celestial giant, Antares, a red supergiant located approximately 604 light-years from Earth. This cosmic behemoth captures the imagination of astronomers and stargazers alike. This stellar titan boasts a diameter roughly 700 times that of our Sun, making it one of the largest known stars in the universe. To put its size into perspective, if Antares were placed at the center of our solar system, its surface would extend beyond the orbit of Mars. This colossal star is not only enormous, but also incredibly bright, ranking among the top 20 brightest stars visible from Earth. Its prominent position in the constellation of Scorpius makes it a familiar sight to many night sky observers. Antares' impressive luminosity, however, is not constant. The star's brightness fluctuates, with its apparent magnitude varying between 0.88 and 1.16. These variations, while subtle to the naked eye, testify to the dynamic nature of this stellar giant. As Antares pulsates and shifts, it provides astronomers with valuable data about the life cycles of massive stars. But what makes Antares truly fascinating is its current stage of life. This red supergiant is nearing the end of its stellar journey, having exhausted its primary fuel source of hydrogen. In the core of Antares, a complex dance of nuclear fusion is taking place. The star is now fusing progressively heavier elements, a process that will ultimately lead to its dramatic demise. This final act in Antares' life is a precursor to one of the most spectacular events in the universe, a supernova explosion. As the star continues to fuse heavier elements, it's building up to a cosmic crescendo that will outshine entire galaxies. When Antares finally explodes, it's expected to become so bright that it could rival the combined luminosity of every other star in the Milky Way galaxy. Imagine looking up at the night sky and seeing a single point of light as bright as our entire galaxy. This is the potential future that awaits us when Antares goes supernova. The explosion will be visible even in broad daylight, turning night into day for a brief period. It's an event that would be remembered for generations, much like the supernovae recorded by ancient astronomers centuries ago. The impending explosion of Antares offers a unique opportunity for scientific study. By observing this nearby supernova, astronomers hope to gain unprecedented insights into the death throes of massive stars. The data collected from this event could revolutionize our understanding of stellar evolution and the processes that create the heavy elements essential for life in the universe. Interestingly, the name Antares itself holds a clue to the star's appearance and historical significance. Derived from ancient Greek, the name means anti-Ares, or rival of Mars. This moniker was given because the star's reddish hue bears a striking resemblance to the red planet. Ancient astronomers noted this similarity, leading to Antares being sometimes referred to as the heart of the Scorpion in its host constellation. The connection between Antares and Mars goes beyond mere appearance. It speaks to the human tendency to find patterns and relationships in the night sky, a practice that has been central to navigation, timekeeping, and mythology for thousands of years. This celestial rivalry between Antares and Mars has been recognized by various ancient civilizations, each incorporating the star into their own cosmic narratives. The anatomy of a supernova. As we venture deeper into the mysteries of stellar evolution, we encounter one of the most awe-inspiring phenomena in the universe, the supernova. This cosmic spectacle represents the grand finale of a massive star's life, a celestial fireworks display that outshines entire galaxies. But what exactly is a supernova, and why does it captivate astronomers and casual stargazers alike? A supernova is, in essence, the largest observable explosion from Earth. It occurs when a star, having exhausted its nuclear fuel, can no longer support its own weight. The resulting collapse triggers a catastrophic explosion that releases an enormous amount of energy and light. This cosmic cataclysm is so bright that it can be seen across vast distances, sometimes even visible to the naked eye during daylight hours. The sheer scale of a supernova explosion is difficult to comprehend. During this cosmic event, material is expelled at incredible speeds, reaching a significant fraction of the speed of light. To put this into perspective, imagine a mass several times that of our sun being ejected into space at velocities approaching 30 million miles per hour. This violent expulsion of stellar material creates shock waves that ripple through the surrounding interstellar medium, shaping the cosmic landscape for light years around. But the supernova's influence extends far beyond its immediate vicinity. These stellar explosions play a crucial role in the cosmic ecosystem, acting as factories for the intense heat and pressure during a supernova create conditions that forge elements heavier than iron, which are then scattered throughout space. This process enriches the interstellar medium with the building blocks necessary for the formation of new stars, planets, and even life itself. The aftermath of a supernova is equally fascinating. Depending on the initial mass of the star, the explosion can result in one of two exotic outcomes: a neutron star or a black hole. Neutron stars are incredibly dense objects where the mass of a sun is compressed into a sphere roughly the size of a city. Their gravity is so intense that a teaspoon of neutron star material would weigh billions of tons on Earth. Black holes, on the other hand, represent an even more extreme outcome. These cosmic enigmas are regions of space where gravity is so strong that nothing, not even light, can escape. They continue to be a source of fascination for scientists and the public alike, challenging our understanding of the fundamental laws of physics. The frequency of supernovae in our galaxy adds another layer of intrigue to these cosmic events. It's estimated that between 2 to 12 stars go supernova in the Milky Way each century. Yet despite this relatively high occurrence rate, no supernova has been observed in our galaxy for several centuries. This statistical anomaly suggests that we are overdue for such an event, heightening the anticipation among astronomers for the next galactic supernova. The last recorded supernova in our galaxy was observed by Johannes Kepler in 1604, more than 4 centuries ago. Known as Kepler's supernova, it was visible to the naked eye for over a year, rivaling the brightness of the planet Mars. The long gap since this last observed event underscores the rarity of visible supernova in our cosmic neighborhood and highlights the potential significance of Antares' eventual explosion. A celestial companion, Antares B. While Antares steals the spotlight in our cosmic narrative, it's not a solitary player in this stellar drama. Hidden in plain sight is Antares B, a lesser-known companion star that adds another layer of intrigue to this celestial system. Described as a little spark of glittering emerald, Antares B is a bluish-white star that orbits its giant red counterpart. The relationship between Antares and Antares B forms what astronomers call a binary star system. These cosmic partnerships are more common than one might think, with many stars in our galaxy existing in pairs or even larger groups. The dance between these stellar companions can have profound effects on their evolution and ultimate fate. In binary systems like Antares, the gravitational interaction between the stars can significantly influence their life cycles. This cosmic tango can alter the rate at which stars age, affect their mass loss, and even determine the nature of their eventual demise. The presence of Antares B adds an extra variable to the equation when considering the future supernova of Antares. The study of binary star systems provides astronomers with valuable insights into stellar evolution. By observing how these paired stars interact over time, scientists can refine their models of stellar life cycles and better predict the outcomes of various stellar scenarios. This knowledge is crucial for understanding not only individual stars, but also the broader cosmic processes that shape our universe. One particularly intriguing example of a binary system on the brink of a stellar explosion is T Coronae Borealis. This system consists of a red giant star and a white dwarf locked in a cosmic embrace that's about to reach a dramatic climax. Astronomers predict that T Coronae Borealis will experience a nova explosion between now and September 2024, offering a rare opportunity to witness a stellar outburst in real time. A nova, while less powerful than a supernova, is still a spectacular cosmic event. In the case of T Coronae Borealis, the anticipated nova is expected to be visible to the naked eye, potentially rivaling the brightness of Polaris, the North Star. This means that for a brief period, observers on Earth will be able to see what appears to be a new star blazing in the night sky. The last recorded eruption of T Coronae Borealis occurred in 1946, making the upcoming event a significant astronomical occurrence. Observers can expect to see this temporary new star with the naked eye for at least a couple of days, and it will remain visible through binoculars for about a week. This provides a unique window for both professional astronomers and amateur stargazers to study and appreciate the dynamic nature of our universe. The rapid nature of nova events adds to their allure. As one researcher notes, this new star will reach its peak brightness within 24 hours of the nova explosion. This sudden burst of light serves as a stark reminder of the ever-changing nature of our cosmos, where stellar dramas unfold on timescales both impossibly long and surprisingly short. While the T Coronae Borealis nova and the potential Antares supernova are different in scale, they both highlight the dynamic and sometimes explosive nature of binary star systems. These cosmic partnerships can lead to some of the most energetic events in the universe, shaping the very fabric of space around them. The cosmic ecosystem, life after supernova. In the wake of a supernova, the universe enters a phase of cosmic renewal. These stellar explosions are not merely destructive events, but rather catalysts for creation on a grand scale. Supernovae play a pivotal role in the cosmic ecosystem, acting as celestial factories that forge and distribute heavy elements throughout the universe. The process begins in the final moments of a massive star's life. As the star exhausts its nuclear fuel, it undergoes a catastrophic collapse followed by an explosive rebirth. This violent event creates conditions of extreme heat and pressure, enabling the formation of elements heavier than iron. These elements, such as gold, silver, and uranium, cannot be produced through the normal fusion processes that occur during a star's lifetime. In the midst of this cosmic crucible, these newly formed heavy elements are violently expelled into space. The explosion disperses material several times the mass of the Sun at incredible speeds, enriching the surrounding interstellar medium. This enriched material becomes the raw material for future generations of stars and planets. The elements produced in supernovae are essential for the formation of planets and life as we know it. Carbon, oxygen, and nitrogen, the building blocks of organic compounds, are among the elements scattered by these cosmic explosions. Iron, crucial for the formation of rocky planets like Earth, is also a product of supernovae. In a very real sense, we are all made of stardust forged in the fires of ancient stellar explosions. This cosmic distribution of elements illustrates the interconnectedness of stellar and planetary evolution. The death of one star paves the way for the birth of new celestial bodies, creating a continuous cycle of cosmic renewal. It's a testament to the dynamic nature of our universe, where destruction and creation are intricately linked. Despite the crucial role supernovae play in cosmic evolution, predicting which stars will go supernova remains a significant challenge for scientists. The difficulty lies in determining the precise stages of fusion occurring within a star's core. Many stars, including red supergiants like Antares, may have millions of years left before they reach their explosive finale. The complexity of stellar evolution makes it challenging to pinpoint exactly when a star will exhaust its nuclear fuel. Factors such as mass, composition, and even interactions with companion stars can influence a star's lifespan and eventual fate. This uncertainty adds an element of cosmic suspense to the study of massive stars, as astronomers watch and wait for signs of impending stellar demise. However, the study of red supergiants like Antares provides valuable insights into the conditions that lead to supernova events. These massive stars are in a critical phase of stellar evolution, having exhausted their primary hydrogen fuel and now fusing heavier elements. By observing the behavior and characteristics of stars like Antares, astrophysicists can refine their models of stellar evolution and improve their ability to predict future supernovae. The data gathered from studying red supergiants helps scientists understand the internal processes that occur in the final stages of a massive star's life. This knowledge is crucial for developing more accurate models of stellar evolution and supernova mechanisms. As one astrophysicist noted, supernovae are indeed fascinating phenomena like no other, and they serve as a reminder of the dynamic processes that govern the universe. Each observation of a red supergiant like Antares adds to our understanding of these cosmic giants. The variations in brightness, temperature, and spectral characteristics provide clues about the internal furnaces of these stars. This information, combined with theoretical models, allows scientists to piece together the puzzle of stellar evolution and supernova prediction. The study of supernova and their progenitor stars has far-reaching implications beyond astronomy. It touches on fundamental questions about the origin of elements, the formation of planets, and the conditions necessary for life to emerge in the universe. By understanding these cosmic processes, we gain insight into our own origins in place in the vast cosmic tapestry. Witnessing cosmic history. The universe unfolds its secrets to us in rare and spectacular events, and few are as awe-inspiring as a supernova in our own galaxy. These cosmic explosions, marking the dramatic end of a star's life, are not just visually stunning, but also scientifically invaluable. Yet despite their significance, observing a supernova in the Milky Way is an exceptionally rare occurrence. Consider this. The last recorded supernova in our galaxy was observed over 4 centuries ago. In 1604, Johannes Kepler documented a stellar explosion that was visible to the naked eye for more than a year. This event, known as Kepler's supernova, rivaled the brightness of Mars at its peak. Since then, our galaxy has been notably quiet, at least from our Earth vantage point. The scarcity of observable supernovae in our cosmic neighborhood makes the potential explosion of Antares all the more significant. If this red supergiant were to go supernova in our lifetime, it would offer an unprecedented opportunity for scientific study and public engagement with astronomy. However, the apparent lack of supernovae in our galaxy doesn't mean these cosmic events are not occurring. Modern technology has revolutionized our ability to detect and study supernovae, even if they're not visible to the naked eye. Advanced telescopes and sophisticated detection methods allow astronomers to observe supernovae in distant galaxies, expanding our understanding of these cosmic phenomena. These technological advancements have opened new avenues for research. Astronomers can now study supernovae across vast cosmic distances, comparing data from multiple events to refine our models of stellar evolution and explosion mechanisms. This wealth of information helps scientists piece together the complex puzzle of how stars live and die. The potential future observation of an Antares supernova would be a game changer in this field. Being relatively close to Earth at about 604 light-years away, Antares offers a unique opportunity for detailed study. Its explosion would provide unprecedented data on the death throes of a massive star, allowing scientists to test and refine their theories in real time. Imagine the wealth of information that could be gathered from such an event. Astronomers would be able to track the supernova's evolution from its earliest stages, observing changes in brightness, temperature, and composition as the explosion unfolds. This data would be invaluable for understanding the physical processes that drive stellar explosions and the formation of neutron stars or black holes. Moreover, the explosion of Antares would offer insights into the production and distribution of heavy elements in the universe. Supernovae are cosmic forges, creating elements heavier than iron and scattering them across space. By studying Antares' supernova, scientists could gain a better understanding of how these elements are formed and dispersed, shedding light on the chemical evolution of our galaxy. The public impact of such an event would be equally significant. A supernova visible to the naked eye would capture global attention, potentially inspiring a new generation of astronomers and space enthusiasts. It would provide a rare opportunity for people worldwide to witness cosmic history firsthand. fostering a deeper appreciation for the dynamic nature of our universe. However, it's important to note that predicting when Antares will go supernova remains challenging. While the star is in the later stages of its life, it could still have thousands or even millions of years left before it explodes. This uncertainty underscores the need for continued observation and study of Antares and other potential supernova candidates. In the meantime, astronomers continue to refine their methods for detecting and studying supernovae across the cosmos. Each observation, whether of a distant galaxy or a nearby star, adds to our understanding of these cosmic events and their role in shaping the universe. A new chapter in cosmic understanding. The study of Antares and supernovae opens a new chapter in our cosmic understanding. These stellar explosions not only distribute heavy elements crucial for planet formation, but also provide insights into the life cycles of massive stars. As astrophysicists refine their models, each observation of red supergiants like Antares brings us closer to predicting future supernovae. This ongoing research enhances our comprehension of the universe's dynamics and our place within it. The potential explosion of Antares represents a pivotal moment in astronomy. It offers a rare opportunity to witness cosmic history and advance our knowledge of stellar evolution. As we continue to explore the night sky, we're reminded of our deep connection to the stars. The cosmic drama unfolding above us is not just a distant spectacle, but a fundamental part of our own story. In the words of one astronomer, supernovae serve as a reminder of the dynamic processes that govern the universe. Close to the blazing sun, a tiny planet holds monumental secrets. Mercury, the smallest and hottest planet, tricked us for a long time, but today space probes have uncovered strange and unexpected surprises. They even suggest the possibility of diamonds existing on the hottest planet.
Scientists have found that a thick layer of diamonds may exist hundreds of miles beneath Mercury's surface.
And that's only scratching the surface. Mercury's internal structure is unusual, too large, too peculiar. What makes it so different from the other planets? And what other hidden secrets might Mercury still be keeping? Mercury, the smallest planet in our solar system, has captivated the interest of astronomers and space enthusiasts for years. Its enigmatic surface, veiled for centuries, only began to unveil its mysteries with the advancement of space exploration technology. The quest to understand Mercury's bizarre landscape started with NASA's Mariner 10 mission in 1973 and continued with the Messenger probe, which launched in 2004. Mariner 10, the first spacecraft to fly by Mercury, provided us with our initial close-up look at this elusive planet. As it passed by, it captured images revealing a landscape covered in craters and unusual ridges, similar to our moon. This mission showed that Mercury had a rough, cratered exterior, along with an unexpectedly strong magnetic field and a much larger core than scientists anticipated. These discoveries reshaped previous assumptions about Mercury's composition. The Messenger mission, formerly known as Mercury Surface, Space Environment, Geochemistry, and Ranging, was launched 31 years after Mariner 10. It significantly expanded our knowledge of Mercury. Unlike Mariner 10, Messenger was designed to enter Mercury's orbit, allowing for an in-depth study of the planet. Over the course of its mission, Messenger captured an astonishing 200,000 images, revealing never-before-seen regions of Mercury. One of the most fascinating discoveries made by Messenger was the detection of unusually high levels of calcium and magnesium on Mercury's darker side. This sparked questions about what processes could create such unusual concentrations. Additionally, the mission revealed that Mercury's magnetic field was notably stronger in its northern regions, a surprising difference from other planets. These findings led scientists to understand that Mercury's interior structure and formation history were vastly different from what they had previously assumed. On planets like Earth, magnetic fields are created by the movement of liquid iron within the core. However, Mercury's internal makeup produces a unique magnetic behavior. What makes Mercury's surface particularly remarkable, though, isn't just the craters and ridges, but also the extreme surface conditions. By day, temperatures on Mercury can reach a scorching 430 degrees Celsius, 806 degrees Fahrenheit. hot enough to melt lead. At night, however, these temperatures drop to an icy minus 180 degrees Celsius, minus 292 degrees Fahrenheit. These wild temperature swings are due to Mercury's very thin exosphere, which provides little insulation or heat retention. Even in these harsh conditions, researchers have found surprising features on Mercury's surface. In 2012, messenger data revealed signs of volcanic activity, including pyroclastic deposits from explosive eruptions. This discovery overturned the long-standing belief that Mercury was geologically inactive. Even more remarkable, in 2020, scientists announced the discovery of water ice in Mercury's polar craters. These permanently shadowed regions are so cold that they can preserve water ice, even though Mercury is extremely close to the Sun. This discovery has led to new speculation about the possibility of simple life forms on Mercury. Could extremophiles, like those that exist in extreme conditions on Earth, be living in these icy pockets? The most recent Mercury mission, Bepi Colombo, was launched in 2018 as a collaborative project between the European Space Agency and the Japan Aerospace Exploration Agency. The spacecraft is expected to arrive at Mercury in 2025. This mission promises to deliver even more detailed data about Mercury's surface, including its chemical composition and geological evolution. From its unexpectedly strong magnetic field to the existence of water ice, Mercury continues to astonish scientists. Now, if you thought Mercury's secrets were done, think again. What you're about to learn will completely flip your understanding of time on this planet, a year shorter than a day. When we typically think of planets, we imagine them spinning once on their axis per day and orbiting the Sun once per year. However, Mercury defies this usual pattern in a very intriguing way. On this small sun-baked planet, a single year is actually shorter than a day. Let's explore this peculiar fact. Mercury completes an orbit around the Sun in just 88 Earth days, making its year far shorter than our own. But here's where it gets even more fascinating. One full rotation of Mercury on its axis, a single day, takes an astounding 176 Earth days. This means that on Mercury, a year is only half the length of a day. This odd scenario leads to some truly strange phenomena. If you were standing on Mercury's surface, you would witness the Sun rise and grow larger in the sky as it slowly moved. At one point, the Sun would appear to stop, move backward for a while, and then resume its usual path. This bizarre movement happens because Mercury's rotation cannot keep pace with its quick orbit. But what causes Mercury's sluggish rotation? Scientists believe the answer lies in a process called tidal locking. Over billions of years, the Sun's gravitational pull has gradually slowed Mercury's spin. Unlike our Moon, which is entirely tidally locked to Earth, Mercury exhibits a 3-to-2 spin-orbit resonance. This means it rotates 3 times for every 2 orbits around the Sun. The extreme nature of Mercury's day-night cycle has intense consequences on its surface. The side facing the Sun is scorched by extreme heat for months, while the night side is left in freezing darkness for an equally long time. These extremes contribute to some of the most dramatic temperature swings in the solar system. As for Mercury's atmosphere, or lack thereof, it is worth noting that the planet's extremely thin atmosphere is called an exosphere. This fragile layer is constantly being lost to space and replenished by various processes such as the solar wind, radioactive decay, and impacts from micrometeorites. Surprising new discoveries have recently been made about Mercury's exosphere. In 2020, researchers analyzing data from the Messenger spacecraft revealed that Mercury's exosphere contains more water vapor than previously thought. This water vapor likely forms when hydrogen from the solar wind combines with oxygen in Mercury's rocky surface. Mercury's short year and long day also have fascinating effects on its magnetic field. Despite its small size and slow rotation, Mercury has a global magnetic field, a finding that surprised scientists. New research indicates that Mercury's magnetic field may be created by a unique dynamo effect in its liquid metal core, influenced by its peculiar orbital and rotational dynamics. This magnetic field, although much weaker than Earth's, plays a vital role in shielding Mercury's surface from the relentless solar wind. Without it, the solar wind would erode Mercury's thin exosphere even faster. Additionally, Mercury's rapid orbit and sluggish spin create opportunities for intriguing observations. Specific points on the planet, known as hot poles, experience the most intense heat because the sun appears to linger in the sky there. On the other hand, there are regions near Mercury's poles that never see sunlight. These permanently shadowed areas are where scientists have discovered signs of water ice. How can water ice exist on a planet so close to the sun? The answer lies in Mercury's orbit and rotation. The permanently shadowed craters at its poles remain in constant darkness, keeping temperatures cold enough to preserve the ice even while nearby areas are baked by the sun's heat. This finding leads scientists to ponder whether other volatile substances, perhaps even organic compounds, might also be preserved in these frozen traps. Mercury's short year and lengthy day also impact how we study the planet. Its fast orbit makes it difficult for spacecraft to reach Mercury, requiring complex maneuvers and multiple flybys of Venus and Mercury itself to slow down enough for orbital insertion. The Bepi-Colombo mission, currently en route to Mercury, will rely on these gravitational assists to adjust its speed and trajectory. Although launched in 2018, the spacecraft will not enter Mercury's orbit until 2025, after completing 9 planetary flybys. Once in orbit, Bepi-Colombo will face another hurdle due to Mercury's unusual day-night cycle. The spacecraft must balance exposure to Mercury's intense heat during the day and maintain power through the long, freezing nights. This delicate operation will be critical for the mission's success, demonstrating the extreme conditions created by Mercury's rotation and orbit. Recent simulations have shed light on how Mercury ended up with such a peculiar rotation rate. These studies suggest that Mercury once rotated more quickly, but its spin was gradually slowed down by the sun's gravitational forces and impacts from large comets or asteroids. Understanding Mercury's slow spin helps scientists piece together not only its history, but also the evolution of other planets in our solar system. As researchers continue to explore Mercury, new mysteries emerge. How does Mercury's core stay partly liquid despite the intense cold during its long nights? What role does Mercury's strange orbit play in its geological processes? These questions remind us that even within our own solar system, many puzzles remain unsolved. Mercury's unique characteristics push us to reconsider how planets form and evolve, encouraging new ideas and theories. Just when you think you've wrapped your head around Mercury's bizarre day, the planet throws another curveball. Its secrets are far from over. A small planet with too many intense secrets. Mercury, the tiniest planet in our solar system, manages to hold an astonishing number of mysteries despite its small size. Scientists continue to be intrigued by Mercury as its distinctive features and unexpected discoveries defy initial expectations. One of the most captivating mysteries of Mercury lies in its unusually large core. Dr. Nancy Chabot, a planetary scientist at Johns Hopkins Applied Physics Laboratory, conducted a study revealing that Mercury's core accounts for about 85% of its total volume. This is significantly larger compared to Earth's core, which only takes up about 15% of its volume. But what caused Mercury to have such an enormous core? One theory suggests that Mercury might have once been a much larger planet, but a colossal collision early in the history of the solar system caused it to lose most of its outer layers. This hit-and-run theory was proposed by Dr. Eric Asfog from the University of Arizona, who believes that a planetesimal struck Mercury, stripping away much of its mantle and crust, leaving behind the iron-rich core that we observe today. Mercury's magnetic field presents another puzzling mystery. Unlike Venus and Mars, which lack global magnetic fields, Mercury generates a magnetic field that is about 1% as strong as Earth's. This unexpected discovery, made by NASA's MESSENGER mission, surprised scientists because they didn't expect a planet as small and slowly rotating as Mercury to maintain a magnetic dynamo. Further intrigue was added by Dr. Katherine Johnson, a planetary scientist from the University of British Columbia. Her team discovered that Mercury's magnetic field is offset from the planet's center by roughly 20% of its radius. This offset could result from variations in the thickness of Mercury's crust, which influences how heat is distributed from the planet's interior. The surprises don't end there. In 2020, scientists announced the detection of volatile elements on Mercury's surface, including sulfur, potassium, and sodium. These elements typically evaporate quickly at high temperatures, so their presence on a planet so close to the sun was unexpected. Dr. Patrick Poplawski from Johns Hopkins Applied Physics Laboratory proposed that comets or asteroids could have delivered these volatile elements to Mercury after it formed. One of the most remarkable recent discoveries on Mercury is the presence of water ice in permanently shadowed craters near its poles. Dr. Nancy Chabot, who was also involved in this research, found that despite Mercury's proximity to the Sun, these craters remain cold enough to preserve ice due to their lack of direct sunlight. Adding to the excitement, scientists have found evidence of organic compounds in the same craters where water ice was discovered. These dark deposits could be complex carbon-based molecules, possibly similar to the ones that may have contributed to the origin of life on Earth. Despite the harsh environment, could Mercury hold clues to the beginnings of life in our solar system? Another significant revelation about Mercury is its unexpected geological activity. For a long time, Mercury was thought to be a geologically dead world, but messenger data indicated recent volcanic activity. Dr. David Rothery from the Open University in the UK found bright spots on Mercury's surface that are believed to be volcanic vents. These features, called hollows, suggest that Mercury could still be geologically active today. One of the most perplexing characteristics of Mercury is its chaotic terrain, an area of disrupted hills and valleys near the South Pole. First observed by the Mariner 10 mission in the 1970s, this region spans an area roughly the size of Texas. Dr. Thomas Waters from the Smithsonian Institution proposed that this terrain might have been shaped by massive earthquakes triggered by the sun's tidal forces as Mercury's orbit shifted. Additionally, recent investigations have uncovered intriguing information about Mercury's structure. Dr. Amir Khan from the University of Zurich utilized data from the Messenger mission to study Mercury's interior. His team discovered that Mercury's core is composed of a liquid outer layer and a solid inner core, similar to Earth's. However, Mercury's inner core is proportionally much larger than Earth's, which could provide insights into some of Mercury's unusual magnetic properties. The fascinating discoveries on Mercury continue to challenge our understanding of how planets form and evolve. Even within our own solar system, there are many unexplained mysteries. Hold on, because Mercury's surface may have shocked you, but what's hidden below will leave you questioning everything. Mercury's hidden depths. Recent investigations and ongoing missions are revealing that Mercury's underground regions hold secrets that are just as fascinating as its surface features. One of the most intriguing aspects of Mercury's subsurface is its core structure. Unlike Earth, which has a solid inner core encased in a liquid outer core, Mercury's core is primarily liquid with a solid inner portion. This unique composition was confirmed by NASA's Messenger mission, which utilized slight variations in Mercury's gravitational field to map its internal structure. The solid inner core of Mercury is estimated to be approximately 1,260 miles or 2,000 kilometers across, accounting for nearly half of the planet's core. In comparison, Earth's inner core only makes up around 20% of its core volume. This difference in proportion plays a critical role in the generation of Mercury's magnetic field, which, although much weaker than Earth's, is surprisingly strong given Mercury's small size. Beneath the crust of Mercury lies a mantle that is thinner than previously thought. Studies now suggest that this mantle might be just 260 miles or 420 kilometers thick, while Earth's mantle measures about 1,800 miles or 2,900 kilometers. This relatively thin mantle has significant implications for Mercury's geological activity and the way heat is distributed through the planet. One of the most thrilling discoveries about Mercury's subsurface was made in 2012, when Messenger detected evidence of ancient volcanic activity. The spacecraft identified shallow depressions, known as hollows, that appeared to form when volatile elements sublimated from the planet's surface. These hollows indicate that Mercury's interior once contained more volatile elements than scientists had previously assumed. In 2020, researchers using Messenger data made another groundbreaking discovery beneath Mercury's surface. They uncovered evidence of a large underground reservoir of magma from Mercury's distant past. This ancient magma ocean likely played an essential role in shaping both the surface and the internal structure of the planet. This ancient magma ocean may explain some of Mercury's unusual surface features, such as the vast, smooth plains covering much of its northern hemisphere. These plains, referred to as the northern volcanic plains, are thought to have resulted from massive lava flows early in Mercury's history. However, the most shocking discovery about Mercury's subsurface came in 2022. Researchers analyzing messenger data found traces of nitrogen trapped below Mercury's surface. This nitrogen may be a remnant of an ancient atmosphere that was driven underground by the intense heat and solar radiation that bombard the planet. The presence of nitrogen in Mercury's subsurface raises intriguing questions about its past. Could the planet once have had a more substantial atmosphere? If so, what might this tell us about its early climate and even the possibility of habitability? Another interesting feature of Mercury's hidden depths is the presence of water ice in craters near its poles, which remain in permanent shadow. Although this ice is technically on the surface, it is hidden from direct view, protected by the extremely cold conditions within these shadowed craters. Some studies suggest that this ice might be relatively fresh, possibly deposited by comets or asteroids within the last tens of millions of years. In addition to water ice, these polar craters are also home to dark deposits that scientists believe might be organic compounds. These compounds, more volatile than water ice, could be remnants of comets or asteroids that impacted Mercury. The preservation of these organic materials within Mercury's subsurface offers a unique opportunity to explore the distribution of organic compounds within the inner solar system. Mercury's subsurface also offers insights into its tectonic history. While Earth has plate tectonics, Mercury does not, but there is evidence of significant contraction as the planet cooled over time. This contraction led to numerous thrust faults, where one section of crust is pushed up over another. These faults, which can be several kilometers high, give us a window into Mercury's subsurface composition and geological past. Recent studies of these thrust faults have revealed something unexpected. Mercury might still be tectonically active. In 2019, researchers found small landforms known as grabens in association with some of Mercury's larger faults. These grabens, which are small valleys formed as the crust stretches, appear geologically young, suggesting that the planet's crust is still moving and shifting. Mercury's magnetic field is another mysterious aspect of its subsurface. While Earth's magnetic field is generated by the movement of molten iron in its outer core, Mercury's magnetic field may be produced by a different process. Some scientists propose that it is generated by a dynamo effect within a thin layer of liquid metal encircling a solid inner core. Another intriguing element of Mercury's hidden depths is the possibility of subsurface faults and fractures that might create pathways for heat and potentially even fluids to move through the planet's crust. Even though Mercury's surface is dry today, some researchers speculate that there could be pockets of liquid water deep beneath the surface, kept liquid by residual heat from the planet's core. The idea of subsurface water on Mercury might sound improbable, but similar phenomena have been observed on other seemingly inhospitable worlds within our solar system. For example, Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans beneath their icy surfaces. Although Mercury's environment is quite different, the potential for subsurface water cannot be completely dismissed. As we continue to investigate Mercury's hidden depths, new questions emerge. How has the planet's internal structure evolved over time? Could there be other volatile elements or compounds lurking beneath the surface? And perhaps most fascinating, what might Mercury's subsurface reveal about the early history of our solar system and the processes that shape the inner planets? These questions underscore the importance of ongoing exploration of Mercury. Each new discovery about its hidden depths not only expands our understanding of this extraordinary planet, but also provides vital clues about planetary formation and evolution throughout the solar system. Looking ahead to future missions and discoveries, one thing remains clear. Despite its small size and proximity to the Sun, Mercury still has many mysteries to uncover. Its hidden depths contain valuable insights into its history and possibly the history of the entire solar system. What a fascinating journey, right? Share your thoughts about what other surprises might be lying in wait on Mercury. Could we find rare minerals or even clues to extraterrestrial life? If you enjoyed this video, don't forget to hit that like button and subscribe to the channel for more updates. Thanks for watching and see you in the next one.
From the outside, You can't tell what is inside a black hole.
What if everything you know about the universe is inside out? Recent theories suggest our entire cosmos could be nestled within a black hole. This mind-bending concept challenges our understanding of space and time, proposing that the very fabric of our reality might be contained within what we once thought was a cosmic destroyer.
So your feet approach the black hole faster than your head does.
Okay.
You snap into
Right.
two segments. Then each of those two segments,
Right.
eventually they snap into two segments. You
Right.
go from 1 to 2 to 4 to 8 to
Right.
16, and you're the stream of particles descending down
Now,
to
is
the
that,
abyss.
are you feeling pain or you're
Yeah!
not?
And in fact, if you want to see a black hole tonight, go outside, look in the direction of Sagittarius. That's where we have the center of the galaxy, and a black hole weighing perhaps 2 to 4 million times the mass of the sun, lurking right at the center of our own backyard.
Black holes, those mysterious cosmic entities, have long been a source of fascination for scientists and stargazers alike. These gravitational behemoths, known for their insatiable appetite for matter and light, might hold secrets beyond our wildest imaginations. But what if they're more than just cosmic vacuum cleaners? What if our entire universe exists within one? This audacious theory raises a central question. Could our entire universe be inside a black hole? It's a concept that turns our perception of reality on its head, challenging everything we thought we knew about the cosmos. As we embark on this journey of cosmic exploration, prepare for revelations that will stretch the limits of your imagination and redefine our place in the universe. Black holes, cosmic destroyers or creators. Black holes have long been viewed as the ultimate cosmic destroyers, voracious entities that consume everything in their path. This perception stems from their most defining characteristic, a gravitational pull so intense that nothing, not even light, can escape once it crosses the event horizon. But what if these cosmic giants are more than just nature's perfect vacuum cleaners? To understand the potential creative role of black holes, we must first explore their formation and nature. Black holes are born when massive stars collapse under their own gravity at the end of their lives. As the star's core implodes, it becomes incredibly dense, creating a gravitational field so strong that it warps the very fabric of space-time around it. This results in the formation of an event horizon, the point of no return beyond which nothing can escape the black hole's grasp. The immense gravitational pull of black holes is a testament to their power. Imagine a force so strong that it can bend light itself, creating a cosmic funhouse mirror effect around its edges. This gravitational lensing, as it's called, is one of the ways astronomers detect and study these elusive cosmic entities. But black holes aren't just found in isolation. In fact, they play a central role in the structure of our universe. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole. These cosmic behemoths can have masses millions to billions of times that of our sun, exerting a gravitational influence that shapes the very galaxies they inhabit. The presence of these supermassive black holes at galactic centers has led scientists to question their role in cosmic evolution. Are they merely the end result of galactic formation, or do they play an active part in shaping the universe we see today? This question challenges the traditional view of black holes as purely destructive forces. While it's true that their gravitational pull is immense, black holes are surprisingly inefficient at capturing matter from large distances. They only consume objects that venture very close to their event horizons. This selective appetite suggests that black holes might have a more nuanced role in cosmic processes than previously thought. In fact, black holes can be sources of incredible energy and cosmic phenomena. When material falls towards a black hole, it forms a swirling disk of gas and dust called an accretion disk. As this material heats up to millions of degrees, it releases enormous amounts of energy in the form of radiation. This process can create some of the brightest objects in the universe, such as quasars and active galactic nuclei. These energetic processes associated with black holes hint at their potential creative power. The radiation and jets emitted by active black holes can influence star formation and galactic evolution, shaping the cosmic landscape around them. In this light, black holes begin to look less like cosmic destroyers and more like cosmic architects, playing a crucial role in the ongoing story of our universe. The idea that black holes might be creators rather than just destroyers opens up fascinating possibilities. Could these cosmic entities be more than just the endpoint of stellar evolution? Might they, in fact, be the birthplaces of new universes? This concept challenges our understanding of the cosmos and raises intriguing questions about the nature of reality itself. If black holes can create new universes, could our own universe be nested within a larger black hole? And if so, what implications does this have for our understanding of space, time, and the fundamental laws of physics? The universe within, a new perspective. The idea that our entire universe could be nestled within a black hole is a concept that challenges our fundamental understanding of reality. This theory proposes that the cosmos we observe and inhabit might be contained within the event horizon of a massive black hole in a larger, parent universe. It's a perspective that requires us to reconsider our notions of space, time, and the very fabric of existence. To grasp this concept, imagine our universe as a bubble floating in a vast cosmic ocean. In this analogy, the surface of the bubble represents the event horizon of a black hole, and everything we know and experience exists within this bubble. The ocean surrounding it would be the larger universe or multiverse that contains our black hole universe. This theory stems from the similarities between the properties of our universe and those of black holes. Both exhibit extreme densities, intense gravitational effects, and mysterious singularities at their cores. The Big Bang, which marked the birth of our universe, shares characteristics with the formation of a black hole, suggesting a possible connection between these cosmic phenomena. One of the key principles supporting this theory is the concept of quantum gravity. This theoretical framework attempts to reconcile quantum mechanics with Einstein's theory of general relativity. In the realm of quantum gravity, the extreme conditions inside a black hole could potentially give rise to a new universe with its own set of physical laws and constants. The implications of this theory are profound. If true, it would mean that the laws of physics as we know them might only apply within our universe bubble. Beyond the event horizon of our cosmic black hole, entirely different rules could govern reality. This concept challenges our understanding of causality and the arrow of time, as events in the parent universe might influence our own in ways we cannot yet comprehend. To visualize this complex idea, consider a Russian nesting doll. Each doll represents a universe contained within a black hole of a larger universe. Our cosmos would be one of these dolls, with potentially infinite layers of reality both above and below us. This nested structure could explain the hierarchical nature of cosmic structures we observe, from subatomic particles to galactic superclusters. The black hole universe theory also offers potential explanations for some of the most perplexing mysteries in cosmology. For instance, it could account for the apparent flatness and uniformity of our universe, as the interior of a black hole would naturally create such conditions. It might also provide insights into the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. Moreover, this concept aligns with the idea of cosmic inflation, the rapid expansion of the universe in its earliest moments. The intense gravitational forces at the event horizon of a black hole could produce an effect similar to cosmic inflation, explaining the uniform distribution of matter and energy we observe in our universe. However, it's crucial to note that this theory remains highly speculative. As one researcher points out, we do not understand how this central singularity works to properly understand the black hole center. This highlights the significant gaps in our knowledge regarding black holes and their implications for understanding the universe. Cosmic incubators, black holes as universe generators. As we venture deeper into the cosmic mysteries surrounding black holes, a revolutionary idea emerges. These enigmatic objects might not just be destroyers of matter, but creators of entire universes. This concept transforms our understanding of black holes from cosmic dead ends to cosmic incubators, potentially giving birth to new realms of existence. The notion of black holes as universe generators stems from the complex interplay between quantum mechanics and gravity. At the heart of this theory lies the concept of Hawking radiation, proposed by the renowned physicist Stephen Hawking. This phenomenon suggests that black holes aren't entirely black, but emit a faint glow of particles over time. Hawking radiation occurs due to quantum effects near the event horizon of a black hole. In this region, pairs of particles and antiparticles spontaneously pop into existence. Normally, these pairs would quickly annihilate each other. However, near a black hole's event horizon, one particle might fall into the black hole while the other escapes, appearing to be emitted by the black hole itself. This process has profound implications for our understanding of black holes and the universe at large. Over extremely long periods, Hawking radiation could cause black holes to slowly evaporate and shrink. This evaporation process might seem to contradict the idea of black holes as universe creators, but it's precisely this mechanism that opens up intriguing possibilities. As a black hole evaporates, it becomes smaller and denser. Some scientists propose that when a black hole reaches a critical size, the immense gravitational forces and quantum effects could trigger the formation of a new universe. This new cosmos would be born from the singularity at the center of the black hole, expanding into its own space-time separate from our own. In this scenario, black holes act as cosmic recycling machines. They consume matter and energy from one universe, only to use that material as the seeds for a new universe. This process creates a fascinating cycle of cosmic birth, death, and rebirth. The implications of this theory extend far beyond a single universe. If black holes can indeed generate new universes, it suggests the existence of a vast cosmic network. Our universe might be just one of countless others, each born from a black hole in a parent universe. This concept aligns with the idea of a multiverse, where an infinite number of universes exist simultaneously. Imagine a cosmic tree with each branch representing a universe and each leaf a black hole. These leaves might sprout new branches, creating an ever-expanding structure of interconnected realities. In this model, our universe could be a single branch on an infinitely complex cosmic tree. This theory also provides a potential explanation for the fine-tuning of our universe. The physical constants and laws that govern our cosmos seem perfectly balanced to allow for the existence of complex structures like galaxies, stars, and life. If our universe is one of many born from black holes, it's possible that each new universe inherits slightly different properties from its parent. Over time, this cosmic natural selection could result in universes increasingly capable of supporting complex structures. However, it's important to note that while these ideas are intellectually stimulating, they remain highly speculative. As one researcher points out, the surprising new insights show that there is still much to learn about black holes. Our current understanding of black holes, quantum mechanics, and the nature of the universe is still limited, and these theories push the boundaries of our knowledge. The concept of black holes as universe generators also raises fascinating philosophical questions. If our universe is indeed nested within a larger black hole, what does that mean for our understanding of reality? Are there layers of existence beyond our perception? Could the physical laws we observe be merely local phenomena with entirely different rules governing the larger multiverse? Living in a black hole, what it means for us. The idea that we might be living inside a black hole seems like something out of science fiction. Yet this theory has gained traction among some physicists, challenging our fundamental understanding of the cosmos. If true, it would revolutionize our perception of reality and our place within it. Living in a universe inside a black hole would have profound implications for our understanding of space and time. The laws of physics as we know them might only apply within our cosmic bubble, with entirely different rules governing the larger reality beyond our event horizon. This concept challenges our notions of causality in the arrow of time, suggesting that events in a parent universe could influence our own in ways we cannot yet comprehend. One of the most intriguing aspects of this theory is its potential to explain certain cosmic phenomena we observe. The apparent flatness and uniformity of our universe, for instance, could be a natural consequence of existing within a black hole. The intense gravitational forces at the event horizon could produce effects similar to cosmic inflation, accounting for the uniform distribution of matter and energy we see around us. Moreover, this theory might provide insights into the nature of dark energy, the mysterious force driving the accelerating expansion of our universe. If our cosmos is indeed nested within a black hole, the expansion we observe could be a result of our universe's growth within its host black hole. This perspective offers a fresh approach to one of the most perplexing mysteries in modern cosmology. The black hole universe theory also opens up fascinating possibilities regarding parallel universes and alternate dimensions. If our universe is one of many born from black holes, it suggests the existence of a vast cosmic network of interconnected realities. Each black hole in our universe could potentially be the birthplace of a new cosmos, creating an infinite fractal structure of nested universes. This concept aligns with the idea of a multiverse, where an infinite number of universes exist simultaneously. In this model, our universe might be just one branch on an infinitely complex cosmic tree, with each leaf representing a black hole capable of sprouting new universal realities. The implications of such a structure are mind-boggling, suggesting layers of existence beyond our current perception. However, it's crucial to acknowledge the limitations of our current understanding and technology. While these theories are intellectually stimulating, they remain highly speculative. Our knowledge of black holes, quantum mechanics, and the nature of the universe is still limited, and these concepts push the boundaries of our scientific understanding. As one researcher points out, we do not understand how this central singularity works to properly understand the black hole center. This statement underscores the significant gaps in our knowledge and the challenges we face in exploring these cosmic frontiers. Our current technology is far from being able to directly observe or test many aspects of these theories, leaving us in a realm of mathematical models and theoretical speculation. Despite these limitations, the idea of living in a universe inside a black hole offers exciting prospects for future research and exploration. It challenges us to think beyond our current paradigms and consider new possibilities for the nature of reality. This theory could potentially provide a unified framework for understanding various cosmic phenomena, from the Big Bang to the large-scale structure of the universe. If proven true, this concept would indeed revolutionize our place in the cosmos. It would suggest that our universe is part of a larger, perhaps infinite, cosmic structure. This perspective could fundamentally alter our understanding of creation, existence, and the very nature of reality itself. It raises profound philosophical questions about our significance in the grand cosmic scheme and the potential for other forms of life and civilizations existing in parallel universes. The horizon of discovery, what lies ahead? The journey to unravel the mysteries of black holes and their potential role as universe generators is far from over. Scientists are embarking on ambitious research projects and experiments to probe deeper into these cosmic enigmas. The quest to understand black holes and their implications for our universe remains one of the most exciting frontiers in modern physics. Current research focuses on several key areas. One primary goal is to detect and analyze gravitational waves produced by black hole mergers. These ripples in space-time offer valuable insights into the behavior and properties of black holes. Advanced detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo are at the forefront of this effort, capturing data from cosmic collisions billions of light years away. Another critical area of study involves observing the event horizons of black holes. The Event Horizon Telescope project, which captured the first ever image of a black hole in 2019, continues to push the boundaries of our observational capabilities. By combining data from multiple radio telescopes around the globe, scientists aim to create even sharper images of black holes and their surrounding environments. However, the path to proving or disproving the black hole universe theory is fraught with challenges. The very nature of black holes makes direct observation of their interiors impossible with current technology. The intense gravitational fields and extreme conditions near the event horizon pose significant obstacles to gathering data. Moreover, the scales involved in these theories are mind-boggling. If our universe is indeed nested within a larger black hole, the parent universe would exist on a scale far beyond our current observational limits. This raises fundamental questions about the nature of scientific inquiry and the limits of human knowledge. Despite these hurdles, scientists remain undaunted. They are developing new theoretical frameworks and mathematical models to bridge the gap between quantum mechanics and general relativity. These efforts aim to create a unified theory of quantum gravity, which could provide crucial insights into the behavior of black holes and the potential for universe generation. Technological advancements will play a crucial role in future explorations. More sensitive gravitational wave detectors, improved space-based telescopes, and in potentially even quantum computers could revolutionize our ability to study cosmic phenomena. These tools may allow us to probe deeper into the nature of black holes and test the predictions of various theoretical models. The implications of these discoveries extend far beyond the realm of physics. The concept of a black hole universe challenges our fundamental understanding of reality, space, and time. It raises profound philosophical questions about the nature of existence and our place in the cosmos. If our universe is indeed one of many nested within black holes, it suggests a vastness to reality that is difficult to comprehend. It opens up possibilities for parallel universes, alternate dimensions, and forms of existence beyond our current imagination. This perspective could reshape our understanding of creation, evolution, and the very fabric of reality. The ongoing exploration of black holes and their potential role as universe generators serves as a testament to human curiosity and ingenuity. It pushes the boundaries of our knowledge and technological capabilities, driving innovation across multiple scientific disciplines. As we continue to peer into the cosmic abyss, we are reminded of the endless possibilities that await discovery. The universe, it seems, is far more complex and mysterious than we ever imagined. Each new revelation opens up new questions, fueling the endless cycle of scientific inquiry and exploration. A universe of wonder. The black hole universe theory challenges our fundamental understanding of reality. It suggests our cosmos might be nestled within a larger black hole, part of an infinite cosmic structure. This concept offers potential explanations for mysteries like dark energy and cosmic inflation. It also raises profound questions about the nature of existence and our place in the grand scheme. While highly speculative, this theory encourages us to think beyond our current paradigms. It reminds us that the universe is far more complex and mysterious than we imagine. As we continue to explore these cosmic frontiers, we're pushed to question our assumptions and expand our understanding. Perhaps one day, as one researcher speculates, we will know exactly what lies inside of a black hole. Until then, we remain in awe of the vast, unknown cosmos that surrounds us.